and at 4 o'clock. And for a detailed agenda of the workshop, please refer to the workshop program. And the report times for each speaker is 50 minutes, and the bell will ring once at 10 minutes and ring twice at 12 and 15 minutes. The group photo will be taken after section 2. So please stay here before the lunch or yes. If you have any questions, please seek assistance for the organizer outside the door. And the first welcome address will introduce our workshop, and the section 1 we will invite our Dean of the College of Engineering is Professor 肖树山肖老师。
Thank you, and I'm very glad to be here and to see our. I think this is the first time the conference, a student conference between us, and and also due to some problems, I know there are many students online in Japan. But I think it's still good, and I wish in the future we can they can come in person. And actually Professor Yang start the one a student exchange of conference I think about 5 or 6 years ago with Kyushu University. 8 years. Time passes so fast. So each year, this year we went to there, and the next year they will come here, and all the details of the conference arrangement will be held by students, and I think it's also a very good training, and also it's good for our students in both sides to know each other. And I'm very happy we can have this event with Tsukuba University, and wish we can continue this program year by year, and even make it bigger. And in NCU we have several professors involved. In the future we will also expect to attend the faculty involved for Tsukuba University. And I think today will be a very wonderful conference, and we will have a party after the conference, and I wish everyone will enjoy it, and wish everyone can get something from this event, especially make friends, and also try to cooperate in the future. And in the last, I wish all will be successful for this event. Thank you very much.
And let's welcome Professor from University of Tsukuba, Akiko Kaneko Sensei.
Good morning, everyone. I'm Akiko Kaneko from University of Tsukuba. Okay. I think. Yeah. And thank you very much for your kind introduction. And now, first of all, I would like to express my sincere gratitude to Professor Yang and all the participants. They organized this first National Central University and the University of Tsukuba joint workshop on some energy technologies. And yesterday, I think we enjoyed wonderful lab tour and also the very wonderful dinner. And I think we deepened our friendship with each other. Maybe student. I heard that the students also enjoyed your great dinner yesterday, and this workshop would not have been possible without the long-standing friendship between Professor Yan and Professor Takada in Kyushu University, and also the Dr. Shen. Unfortunately, Dr. Shen and several students cannot join this workshop on site, but I would also thank you for taking this into consideration and implementing the hybrid. Okay, and by chance, in April in this year, National Central University and the University of Tsukuba have successful conducted international exchange agreement. And originally, this agreement was to be concluded a little bit earlier, but due to the COVID-19, it is delayed. It was delayed, and we are very happy to have this workshop during this memorable first year. Finally, and okay, so I think I will briefly introduce my university. So where is the University of Tsukuba? So you can find this. It is Japan, and you can find here. Sorry, maybe I feel it. Okay, this is Tokyo area. Here is the Tokyo. And this is Ibaragi Prefecture, and we can find this is Tsukuba City, and we have a university this area, and our building is here. Okay, and here's the history of University of Tsukuba. And the University of Tsukuba was originally started as Tokyo University of Education, which opened in 1949. And it was later opened as the University of Tsukuba in 1973. So this year we have our 50 years celebrations anniversary of the university in October. And currently the university consisted of the number here that more than 2,300 faculty members, 3,000 staffs, and almost 10,000 undergraduate students and 7,000 graduate students. And we have also, here's some Nobel Prize winner over faculty members. And this is the education organization of the undergraduate students. You can find we are belonging to this School of Science and the Technologies, and what makes it unique is that it is a general university that include the School of Medicine and the School of Physical Education and the School of Art. And there's we have many graduate Olympics and the Paralympic medalist in Japan we have. And also here's here's the educational organization of graduate students, and we are belonging to the here Graduate School of Science and Technologies. And here this is the department. We named it degree programs in systems in information and engineering, and we are here. And there's now almost 200 students and the 30 faculty members and the 9 collaborative professors here. And our master's and the doctoral programs in engineering, mechanics, and energy provides education and research oriented toward harmony among humans, society, and the environment, and effective use of resource in the fields of space development, engineering, energy, and the environment, and the disaster control, and the multi-scale solid materials. So you can find that this department is thus structured differently from a typical mechanical engineering department, and it's a program that integrates different field of research, like interdisciplinary research. And also, we often collaborate with the national institute, such as JAXA and ICE and PWRI and the JA and so on. So we have many such a national institute surrounding the university. Here's the university, and we can find such a national institute over Japan in many numbers over there. Yeah. Okay, so I think it's almost time, but okay, this is my laboratory's concept, research concept. So, and there's many topics about thermal fluid engineering, and this is divided by almost 4 big research projects. One is the energy system engineer, is space environment utilization technology development, and microthermal and fluid engineering, and the development of technology to reduce environmental impact. And I am very glad to introduce several of my our research topics today, and please enjoy, and thank you very much.
Thanks for Conical Sciences opening. Let's welcome the Section 1 Chair, Tsukuba Ken.
Okay, thank you. My name is Ken Tsukahara. I'm a chairperson of this first session. Then, so this session presenter, please. So the first presenter, Kang Fu-san. So, are you ready? Okay. So the title is Flowing Heat Transfer Performance Comparison of Skype Straight and CNC Diverging Microchannel Heat Sinks. Okay.
So good morning, everyone. My name is Kang Fu Song, and I'm from the National Central University. So today I'd like to talk about flow-borne heat transfer performance comparison of Skype straight and CNC divergent microchannel heat sinks. So in recent years, due to the rapid growth of the global internet traffic, like the social networking, online gaming, or web meeting, the global data center processing load has increased. So today, most current data centers use the direct air cooling method. However, due to a low thermal conductivity and low heat capacity of air, the air cooling causes a large flow resistance when it flows through a long flow path inside a server, and a lot of electronics are on the way. Then a lot of fan power will be consumed. The power consumption for data center operation will increase drastically, and more than 50% is used in the air cooling system. Although they have seen a lot of innovation improvements over the last decade or so, it seems like the air cooling method is on its last legs. So to give a higher energy efficiency on data center cooling, some advanced cooling methods should find out. So to replace the air cooling, the most common advanced cooling technology that can deliver high flux is the liquid cooling or the two-phase evaporative cooling system. So instead of low thermal conductivity and low heat capacity of air, the liquid cooling or the two-phase evaporative cooling systems have the higher transfer performance due to their high transfer coefficient. And the systematic diagram is shown here, and we can see that usually the cold plate will place on the heating source, the CPU, and the heat will transfer from the heating source to working fluid. The working fluid will be carried by a liquid pump to a remote exchanger and dissipated heat to the atmosphere by a fan. Usually for a single chip, if the heating rate is below 500 watts, then the liquid cooling is enough. However, if the heating rate is over 500 watts, then the two-phase evaporative cooling system will recommend. We can take a 1 kilowatt heat expansion, for example, to compare these two different. If we take the water as a working fluid and we know the properties, then we can get the required mass flow rates. So the answer is that once when we use the two-phase evaporative cooling system to dispatch 1 kilowatt, the required mass flow rates will much lower than that of use in the liquid cooling system. And this means that we can get a small cold plate size and lower pumping power in a two-phase evaporative cooling system. However, when we use the cold plate in the two-phase cooling, there is a flow reversal challenge. And these graphs show some of the common cold plate used in the two-phase applications industry. And in 2009, Lee and Woodward showed the visualization of the flow reversal phenomenon in the microchannel heat sink. At the first beginning, once the flow reversal occurred, the bubble will generate from the channels and flow reverse into the inlet manifold. Then the upcoming liquid will be blocked by these bubbles. So the channels will gradually become dry out until the pressure of the refreshed liquid at the inlet increase enough to push the bubble vapor again to lift the channels. So this flow reversal problem will degrade the heat transfer performance of the cold plate. So to solve the flow reversal problem, we designed the divergent channel inside the cold plate. So this is the test section. The test sections included the CNC divergent and the sky straight channels, the commercialized sky straight channels. So the heating area here, the yellow block is the heating area. So the working fluid coming from the inlet distribution zone here, and it will flow through the channels and reach the returning zone. Then since it is a two-pass flow configuration, so it will become a U-turn, the flow will become U-turn and keeps going and through the outlet, as we can see in the red arrow. So from the size table, we can see that for the outer size, for both of the channels is 68 times 56 millimeter square, and for the channel height is 4 millimeter. And for the channel width, for the straight channel, because it's a commercialized one, so it is about 0.35. And for the divergent, is from 0.6 at the inlet, and at the outlet is 1.4 millimeter. And for the channel wall thickness, for the straight channel is about 0.15, and for the divergent is about 0.5. And also for the total heat transfer area in the straight channels, it is about 30,000 millimeter square, and for the divergent one is about 13,000 millimeter square. And this is the assembly test sections. It is attached on the Intel CPU thermal test vehicle, TTV, which was used to simulate the thermal characteristic of a CPU. So the working fluid we choose is the R245A, which the flow rate is 300 ml per minute, and the saturation temperature is from 23 to 35 degrees as the heating rate increased during the heating time. And two temperature points are measured on the TTV, the TCAS center temperature and the TCAS max temperature. The TCAS center temperature is measured at the center position of the TTV, and the TCAS max temperature is measured after the center position along the flow path. And also for the thermal resistance, we defined as the temperature difference over the heating rate. So we can see the experiment results that we compare the thermal resistance for the divergent channels and the sky straight channels at various heating rates. And we can see that there's a 38% difference at lowest heating rate, and it gradually comes to the same point at the highest heating rate. The reason is that at the lowest heating rate, a lot of bubbles were generated inside the straight channels. So some part of the straight channels will be clogged by the bubbles, and it will have some of the dry out happen. So we can see that the straight channels, the thermal resistance increase as the heating rate increase. However, for divergent channel, since the divergent channel is the expanding channel, so the expanding channel that the bubble can easily move to the outlet, so it will defer the partial dry out. The bubble will easily move to the outlet, so it defer the partial dry out. So thermal resistance will decrease as the heating rate increased. Also, for the maximum thermal resistance, we can see that the heat transfer characteristics is almost the same as the previous one. But since the TCAS max temperature is measured here is after the center position along the flow path, so it implies that more channels will dry out. So that means that it induced a much higher thermal resistance in this graph. And also, since the divergent channels can easily move the bubbles to the outlet that it can mitigate the flow instability. So that means that we can see that the heating rate at over 1 kilowatt, the thermal resistance of the divergent channels is lower than that of the sky straight channels. And in addition to the thermal resistance, the pressure drop and the pumping power are also another important factor to the heat sink design. And we can see that for the pressure drop, the sky straight channels, this one is much larger than a divergent channel because that the channel width of the sky straight channels is much smaller. So that means that there's a 30% to 48% higher that of the sky straight channels is much higher than that of our divergent channels. And also for the pumping power, we can see that the pumping power required for a divergent channel, the triangular one, that is generally lower than that of the required for the sky straight microchannel heat sink. But we can see that for the result, we can see that since that the sky straight channels, the thermal resistance is much lower than that of our divergent channels. But the basis of the comparison is not the same. So we can see from the size table that the channel width and the channel walk thickness for both of the channels are not the same. So of course the total heat transfer area is not the same. It is about 2.3 times different. So to make the same basis of a comparison, so we redesigned the microchannel heat sinks to make the same basis. So now we have two options. One is to let the size condition of the divergent channels be similar to the straight one, but this will give some problems like the inlet pressure drop will increase or the probability of the bypass flow across the adjacent channels will increase. So we choose the second options, that is to let the size condition of the straight channel be similar to the divergent one to make the same comparison standard. So this is our succeeding research. We make the same basis of comparison. And of course that this is the microchannels, and the yellow block here is the heating area is 40 times 40 meters square. So the working fluid still coming from the inlet distribution zone and flows through the channel and reaches the returning zone, and it still keep going for flow through the outlets. So the inlet is 0.6 and going at 1 millimeter at the returning zone. And since it's a two-pass flow configuration, so of course that is still make a U-turn and flows to the outlet at 1.4 millimeter. And this is our succeeding microchannel heat sink. So it has a channel plate, a covers plate, and a gasket that is placed between the channel plate and covers plate to prevent the bypass fluid across adjacent channels. So the working fluid coming from the inlet header and flows here to the inlet distribution zone. Then it is heated and evaporated into a two-phase condition in the channels, and then it will go by U-turn, as we can see in the graph A, like go by U-turn in the returning zone, and flows to the end of the wall at here B, and we can see we can make an upright turn and make a right turn, and then the exit mixing zone will collect the liquid vapor mixture from the exit holes here, and totally flows out from the exit manifold. So this is our results. We do again. So of course we choose the same working fluid as our R245FA, which with the saturation temperature of 30 degrees and the flow rate of about 300 ml per minute. And also we can see the size table that all of the information of the size for the divergent channels and straight channels now is the same, of course, including the total heat transfer area. So we can see from the results that the y-axis is the heat transfer performance, and the x-axis is vapor quality. You can see that the heat transfer performance for the divergent channels, the orange, the circular one, is the same as the straight channels and low vapor qualities, but it differs to the partial dry out at high vapor quality, because that the divergent channel, we know that it has the expanding channel, so the bubble can easily move to the outlet. So it differs the partial dry out. So that means that at high vapor qualities, at high heat flux conditions, that the bubble will not easily block in the channels and will move to the outlets, not like the straight one. Also, we can see from heat transfer performance that the divergent one, the maximum heat transfer performance for divergent is 20% higher than the straight channels, and also for the maximum partial dry heat flux, that is point, and this point, the partial dry heat flux is about 27% difference. So we can see that the divergent channels could indeed release the bubble vapor pressure downstream and increase the flow stability. That means that we can easily move the bubble to the exit and not to block inside the channels, especially at high flux conditions. That means here you can defer the partial dry outs. So the summary, the first that our study that just compared the flow-borne heat transfer performance of refrigerant R245A in two-pass divergent microchannel heat sink and with the commercialized one. And although the results show that the commercialized capture channels have the 28% lower to 40%, 4.2% higher than that of the divergent heat sink, but the basis of comparison is not the same. So we redesigned the microchannel heat sinks. So the succeeding research showed that the divergent channels could indeed release the bubble vapor pressure downstream and increase the flow stability, especially at high flux conditions. So it is possible to reduce the channel width of the divergent channel heat sink to increase the heat transfer performance. Thank you very much.
Thank you for presentation. So, and do you have any questions?
Thank you very much for your interesting talk. And I have one question. In order to use your system for in the engineering field, how what is what you plan that if you increase the heat transfer rate or something, you scale up this system, or you use the number of this system like a parallel?
Oh, because that our study just because that now the for the microchannel heat sinks that usually in the commercialized one is the straight channels. Is that this one? This is some companies do. Yeah. So especially that easily the bubble can be blocked in the inside channels. So the heat transfer performance, that the heat flux, the heating rate is not very high. So we redesigned the microchannel heat sink. That of course that it might get the flow instability, but the heating rate may be higher than, maybe this one can be higher than the value about the 1.2 or 1.3 kilowatts. Yeah, but if you still increase your heating rate, maybe we need to get a number of the microchannel heat sinks, not use a single one. Yeah, in the two-phase system.
Thank you very much.
Okay, so it's late. So thank you for your presentation. Next, so each one Chan. Are you ready? Okay. So, the title is for heat transfer performance on plane and microporous coated two-pass divergent microchannel heat sinks.
Okay, thanks Chair's introduction, and I'm Yichuan Zhang, and my topic is flow boiling heat transfer performance in plane and microporous coated two-pass divergent microchannel heat sinks. And from this report, we know that flow boiling in microchannel can handle with high heat flux encountered in the electronic cooling. And although there is flow reversal problem while flow boiling in a microchannel, they will degrade the performance. But the divergent channel can solve this problem to some degree. So it seems that we can further apply some heat transfer enhancement method to it to achieve higher efficiency of heat exchanger to save energy usage. And there are two kinds of enhancement surface that is already used in flow boiling that we can choose from. One is structure and the other is porous. For the structure surface, they are spread with the processed cavity. Its cavity size can be designed according to the working fluid we are going to use. And for the porous one, the cavities are produced by arbitrary stacking of the particles, so it will have a wider size distribution. And both of them are increase the heat transfer performance by increase the nucleation site. And in our lab, we have tested the enhancement surface pool boiling heat transfer performance. Here shows the heat transfer coefficient versus the heat flux. And dark circle represent the smooth, that means the plane surface. There's the enhancement surface. And we can see that the heat transfer coefficient is higher than the plane one over the whole heat flux range. But for the microchannel, the structure surface is difficult to be processed on due to the limited space. So it seems the porous surface will be a better choice. And we know porous surface have a lot of nucleation sites on it. However, for a certain superheat is required for the boiling to occur. And we can see the curve shown here. These represent the temperature distribution start from the heating wall toward the free surface at the saturation temperature. And here shows the thermal boundary layer thickness. For the traditional porous surface, the thickness of its structure will be thicker than the thermal boundary layer. So the cavity created above the thermal boundary layer thickness will never be activated. So the structure above this thermal boundary layer thickness will only be an additional thermal resistant. And also, the bubble will be blocked. The bubble that is nucleated at the lower part will be blocked by this structure. So it is not good for the heat transfer. So Chen and Yu propose a micropolar surface concept is that the structure should be all within the thermal boundary layer thickness, so that it can reduce the thermal resistance and also the vapor leaving path. So we will, in our research goal, we would like to use the aluminum powder with 16 micrometer average particle size to make a 45 micrometer thick micropolar surface on the two-pass divergent heat sink and to explore its heat transfer characteristics. And here shows the particle distribution of the particle that we use, which average size is about 16 micrometer. And for the coating thickness, we will estimate the thermal boundary layer thickness by assuming the linear temperature distribution in the liquid and cooperate with the turbulent force convection correlation to estimate the thickness of thermal boundary layer thickness. And this coating thickness is thinner than the estimated one. And for the coating surface, we will first mix the aluminum powder with the bonder and the carrier MEK together. And with the help of high pressure air and the spray gun, the solution will be sprayed onto the surface of our heat sinks that is placed on the coating platform here. And after that, the heat sink will be put into the oven and be cured at 220 degrees Celsius for 3 hours. And here shows the heat sinks after coating. The gray part is the coating, the surface with coating. And here I shows the measuring points. And I take the first pass at the channel fault as example. Here is the measuring point, and I will measure the depth between the channel bottom and the channel wall tip before and after coating. So the difference of these two values will be my coating thickness. And the average coating thickness is 45 micrometer with 15 micrometer standard deviation. And here shows the SEM image of coated copper plate. And we can see there are many cavities on this surface, can be served as the potential nucleation site. So we will have two heat sinks. One is with coating and the other is without coating. And both of them will be tested on this system. First, the liquid will be pumped through the flow meter and preheater to our required subcooling temperature. And the liquid will be evaporated by absorbing the heat transferred by the copper rod to the vapor phase. And then the vapor will be condensated in the condenser to the liquid phase to fulfill a cycle. The working fluid we use is refrigerant, and the temperature is 30 degrees Celsius. And there are 3 different flow rates we test. And this is our test result. Here is the comparison between the microporous coated at the lower flow rate, 100 millimeter per minute. And here shows the heat transfer coefficient varies with the heat flux. The red for the plain surface and star for the coated surface. And we can see both of them heat transfer coefficient increase with the increased heat flux, decrease at some point, and decrease is due to the dry out occur. And also you can see that for the coating surface, it has a higher heat transfer coefficient before dry out occur. And take this heat flux example, the enhancement is about 68%. This is mainly due to the greater nuclear on the coating surface, so it will have a higher heat transfer performance. So due to more nucleation size, so the bubble will generate vigorous. So the dry out so the bubble will easily block the channel. So the dry out occur at a lower heat flux in this case. Okay, then we see the pressure drop. Again, the pressure drop will also increase with increased heat flux due to the higher vapor shear. And we can also see the coating surface will have a higher pressure drop. This is due to the vigorous bubble generation, so the flow will be more complex. So pressure drop will be higher. And also at the same, this heat flux here, the pressure drop will increase about 40%. And for the median flow rate, similar trend we can observe, except for the higher heat flux for the coating surface, the heat transfer coefficient will stall at a higher heat flux. This is due to that at a higher heat flux, the flow reversal will become severe, and it will deteriorate the heat transfer. So the heat transfer coefficient will be stalled. And also, again, for the same heat flux comparison, the heat transfer coefficient will increase about 30%. The pressure drop at the same heat flux also increase about 30%. And for the high flow rate, 273 millimeter per minute, again, they shows the similar trend, but at this case, we can see the dry out will occur at a similar heat flux. This is due to that at a higher flow rate, the inertial force become greater. So it can overcome the flow reversal to avoid earlier dry out. And also at a higher flow rate, the convective voiding become important. So the enhancement become lower for the higher flow rate case. And at this heat flux, the enhancement become to only 17%. And at this heat flux, the pressure drop increase about 30%. Okay, and here shows the effect of different flow rates on the coating surface. And we can see for the heat transfer, there are 3 trends. First, linear increase, and then also linear increase, but with a lower slope, and then decrease. First, there are more bubble generated due to the more cavity are activated. So we will have a higher heat transfer coefficient here. And at the median heat flux, to the flow reversal, it will degrade the performance, so the increment will be lower. And finally, dry out occurs, so the performance will drop. And for the pressure drop, just as expected, for the higher flow rate, you will have a higher pressure drop. And so for the summary, At the higher heat flux, flow reversal will affect the enhancement of the porous surface, and the pressure drop will increase from 30 to 40% with the microporous coating, and due to the more complex flow. For the heat transfer rate, it can increase 17 to 68% by the coating surface, and due to the greater nucleation side. However, more bubble generated, so the dryout may be occur at a lower heating rate. And thank you. This is my presentation.
For your presentation, and do you have any questions?
Page 9. And let me see. Okay, page. I find that you point out that the 25.8 is the heat flux or heat transfer coefficient?
The heat transfer coefficient. Oh,
So
sorry.
what problem you got?
I'm missing the K here.
Yes, you make the wrong dimension, right?
Yeah.
Okay, and the next page, let me see. So, well, the pressure drop, is this 6.11? Is that correct? I find that the dimension is the value is the more than 10, right? Almost 15.
Yeah.
Yeah, so what's the problem?
I miss. I make a wrong value here, but I sure that the pressure drop will increase same as 30%.
What's the value of this one?
This is about 17 kPa and 17 and about 13.5.
13.5. Okay.
Thank you.
Any other question?
Have you tried a different fabrication condition for different porosity and pore diameter? Yeah, for your structure.
You mean
Different porosity, different pore diameter. Yeah, have you tried?
No.
Okay.
Just
because of the fabrication limitation or something.
sorry again.
Okay. Yes. You only try one case. That's
Yeah.
because you cannot control the porosity or diameter based on your fabrication process.
Porosity. I can adjust the particle size, but I use this because I have seen the paper that if the particle size becomes smaller, the heat transfer enhancement will be lower, and for this size have maximum enhancement for this size. And also in our lab, we previous use this kind of enhancement method. We also use this particle size. So I choose this particle size.
Okay. Thank you. So it does 50 times a minute. Okay. So next presentation. Third presentator is Sean Wu. The title is an experimental study on heat pipes for low temperature applications.
Thank you for introduction. Today I'm talking about an experimental study on heat pipes for low temperature applications. My name is Haoxuan Wu. Due to the increasing popularity of the cold-chain transportation and communication satellite applications, most of these applications operate within the temperature range of -20 to -40 degrees Celsius. Currently, electronic devices are using coupled heat pipes as a cooling tool. They use the heat pipes to transfer the heat from the circular board IC to the component's case. But when using in the low temperature applications, water may freeze below 0 degrees Celsius, causing the heat pipes to malfunction and affect heat transfer performance. Here collect some paper for heat pipe thermal performance at low temperatures, and we can observe the working fluid usually use methane, ethane, and ammonia. However, it is a few research have been conducted in a temperature range of -20 to -40 degrees Celsius. Only Latawu et al. Had a research in 2010. So this and to find out the most proximate working fluid applied in this temperature range. The thermal performance of the heat pipe is affected by the working fluid vapor pressure gradient, thermal conductivity, and the liquid transfer parameter. And the liquid transfer parameter is defined as the liquid density times the surface tension and latent heat. Then define the liquid viscosity. High vapor pressure gradient can help the heat pipe start up, and the liquid transfer parameter can help the heat pipe get more capillary force. According to the fluid property, select some working fluid as suitable to use. And among this fluid, the vapor pressure gradient between the acetone and methanol is too low, and ammonia is toxic, and ethane and ethylene are flammable. So R245FA, R134A, and R32 has suitable as the select as a suitable working fluid in this study. We use two sinter-coupled heat pipe with a diameter of 10 mm and 12 mm in this study, and the heat pipe total length is 37 cm. The length of condensing section of the heat pipe is 6 cm, and the length of the evaporating section is 31 cm. And we use a 5T type thermocouple to measure the local surface temperature of the heat pipe. And one thermocouple attached on the condensing section, and 4 thermocouple were attached on the evaporating section. This graph shows the schematic of the experimental system. The condensing section of the heat pipe was inserted in the hole of the copper block, and the other side of the copper block was connected to the evaporator coil from the refrigerator to keep the condensing section of the heat pipe at a temperature -40 degrees Celsius. And the heating wire was wound on the evaporating section surface of the heat pipe, and the input heating power was controlled by the power supply. And my thermal resistance is defined as the temperature of the evaporating section on the 36 cm minus the temperature of the condensing section, then define the heat transfer rate. And filling ratio is defined as the ratio of the refrigerant charge to the maximum refrigerant charge in the evaporating section times 100%. Here is my experimental result. Here shows the thermal resistance with the heat transfer rate of the 10 mm and 12 mm using refrigerant R245FA with a different filling ratio. In the 10 mm heat pipes, the minimum thermal resistance is 0.251 degrees Celsius over watt for a filling ratio 30.2%. And in the 12 mm heat pipe, we test the 6 filling ratio, and the minimum thermal resistance is 0.129 degrees Celsius over watt for a filling ratio 33.4%. And here shows the thermal resistance with the heat transfer rate of the 10 mm and 12 mm heat pipe using refrigerant R134A with a different filling ratio. In the 10 mm heat pipe, we test the 5 filling ratio, and the minimum thermal resistance is 0.137 degrees Celsius over watt for a filling ratio 29.9%. And in the 12 mm heat pipe, the minimum thermal resistance is 0.110 degrees Celsius over watt for a filling ratio 41.4%. And here shows the thermal resistance with the heat transfer rate of the 10 millimeter heat pipe and 12 millimeter heat pipe using refrigerant R32 with different filling ratio. In the 10 millimeter heat pipe, the minimum thermal resistance is 0.065 degrees Celsius over watt for the filling ratio 26.2%. And in the 12 millimeter heat pipe, the minimum thermal resistance is 0.085 degrees Celsius over watt for a filling ratio of 46.1%. And here shows the change of the minimum thermal resistance with filling ratio of the 10 millimeter and 12 millimeter with the different refrigerant. In these two graphs, we can observe the refrigerant R32 has the lowest thermal resistance, and R134 is the second, and R245 has the highest, and 12 millimeter is the same. This is because the R32 has the best property of the vapor pressure gradient and the liquid thermal conductivity and the liquid transfer parameter compared to the refrigerant R134A and R245FA. In addition, we can observe when changing the filling ratio has a significant impact for R245FA. This is because the R245FA's vapor pressure gradient is only 0.14 times of the R134A and 0.04 times for the R32. And it is R245A's liquid viscosity is 2.5 times higher than R134A and 4.8 times for the R32. It's leading to the when using the refrigerant R32 change the filling ratio will thermal resistance variable higher than R134A and R32. And here shows the change of the minimum thermal resistance with the filling ratio using a refrigerant R245FA and the R134A with a different diameter. In the result, we can observe the 12 millimeter heat pipe thermal resistance is lower than 10 millimeter heat pipe. This is because when the heat pipe diameter increases, the heat transfer area of the liquid vapor interface rises, leading to the decrease the evaporating and condensing thermal resistance. So this result is when reduce the thermal resistance for R134A and R245FA with increasing the heat pipe diameter. And here shows the change of the minimum thermal resistance with the filling ratio using the refrigerant R32 with a different diameter. And we can observe here is a 10 millimeter heat pipe thermal resistance is lower than 12 millimeter heat pipe. And this is because the 12 millimeter heat pipe wick thickness is bigger than 10 millimeter heat pipe wick thickness. So it is leading to 12 millimeter heat pipe thermal resistance is higher than 10 millimeter heat pipe. And another one reason is the R32's fluid property is better than R134A and R245FA. So this to thermal resistance of the R32 heat pipe significantly influenced by the thickness of the heat pipe wick. So 10 millimeter heat pipe using R32 has a lower than 12 millimeter heat pipe. This is my conclusion. When design a heat pipe, we can consider the vapor pressure gradient, liquid thermal conductivity, and liquid transfer parameter of the working fluid is beneficial for selecting the approximate fluid. Refrigerant R32 has the lowest thermal resistance. The R134A is the second, and R245 has the highest. R32 has the best property of the vapor pressure gradient, liquid thermal conductivity, and the liquid transfer parameter compared to the refrigerant R134A and R245FA. As the heat pipe diameter increases, the heat transfer area of the liquid vapor phase rises, leading to the reduce the thermal resistance for R134A and R245FA with the increasing heat pipe diameter. The thermal resistance of the R32 heat pipe is significantly influenced by the thickness of the heat pipe wick. The 10 mm heat pipe had a lower thermal resistance than 12 mm heat pipe. This is my presentation. Thank you.
Thank you for your presentation. The schedule is late, so I'm sorry, but only one question, please. Any other questions? Oh, okay. So please, Professor Shem.
Okay. Can you hear my voice? Yes. Can you hear my voice?
Yep.
Okay. Okay. Thank you for the very interesting talk. I'm just have a small question. I think it's probably the last slide you show. The difference between the 10 millimeter and 12 millimeter heat pipe result for R32. Like why there is not much difference?
Can you speak again? Sorry.
Yeah, like I think with the other two like refrigerants, there is a big difference when you change the heat pipe size, right, from 10 millimeter to 12 millimeter. But with R32, there is not much difference.
Because when I test the R32's full property is better. So the heat pipe weak part thermal resistance is much percent in the total thermal resistance. And the 12 millimeter heat pipe weak part thermal resistance is higher than 10 millimeter heat pipe weak part thermal resistance. So in the total thermal resistance, the 10 millimeter heat pipe thermal resistance is lower than 12 millimeter heat pipe.
Yeah, but if you go back like one slide with different refrigerants, you see much bigger difference, right?
Because when test in the R245FA and R134A, the total thermal resistance is influenced by the working fluid, not the weak part thermal resistance. So when test the R32, it's different with the R245FA and R134A.
Right. Like if I may, I have another question. Like so in your conclusion, like you think the thermal resistance has to do with these three thermal physical properties, right? Like exactly how do these three thermal physical property impact thermal resistance? Is there like do you think you can come up with a kind of a non-dimensional number that includes all these three thermal physical properties that can explain the difference in thermal resistance?
Sorry, can
Yeah, like here, like you focus on the three thermal physical properties, right? Like exactly how do these three thermal physical properties affect thermal resistance?
no 有一点不懂。
It's okay. Maybe I can ask you next year when you visit Tsukuba. Okay, thank you very much. 深野君、以上ですよ。
Thank you for your presentation. So the next is next. So next presenter is Yang Chen Zhang, and the title is experimental study on thermosiphon battery cooling module.
Thanks for introducing. Hello everyone, my name is Yan Chen Dong from National Central University. Today, I'm going to an experimental study on thermosiphon battery cooling module. With the rise of environmental awareness, renewable energy has become the mainstream energy in the future. Renewable energy is not always available, so we can use battery energy storage systems to store energy, then it can be used whenever it's needed. This picture shows the Tesla Megapack, and it included the black one here is their solar panels, and the white box here is the battery energy storage systems. They use battery energy storage systems to store the solar energy. And the picture here is the power consumption in a day. It's from Taiwan Power Company. The vertical axis is energy used, and the horizontal axis is time of a day. Blue line here is the total power consumption, and the red line here is the solar energy supply. As we can see, if we want to use the solar energy as the mainstream energy in the future, we can use battery energy storage systems to store energy and use it at night. And here's the inside view from Tesla Megapack. As we can see, a whole Megapack has a lot of battery module, and for one battery module has a lot of lithium batteries. And the heat generated by one lithium battery increases when the charging and discharging rate increases. So how to dissipate heat in the battery module is an important issue under fast charging and discharging. And battery energy storage systems is also widely used in electric vehicle. And due to the need for fast charging and discharging, lithium battery pack thermal management systems are widely used in electric vehicle. The left-hand side is the Tesla Model Y, and the right-hand side is the Model Y's battery pack from Paul Kelly. And as we can see here, the gray circle here is the lithium batteries, and the gray plate here is their cooling water channel. They use the cooling to cool down their battery pack. And for the current cooling method, we can separate it by three parts. One is air cooling, another is liquid cooling, and the last one is phase change materials. For air cooling, they are all doing an experiment for the air cooling. The problem of air cooling is in the middle section of the battery pack. The compressed flow may cause high flow resistance in the middle section, and it may cause high pressure drop. And for liquid cooling, this is the schematic diagram for Tesla liquid cooling system. The black line here is their cooling water channel, and the black circle here is their lithium batteries. And for liquid cooling, the compressed piping can cause more pressure drop, and there is a risk of liquid leakage. And for phase change material, Roy are also doing experiments for phase change materials. They often use natural convection, but during continuous charging and discharging, the absorbed latent heat may not have enough time to dissipate. And after knowing current cooling method, we should know what temperature range we should control our batteries. And here the test is the operating temperature for 18650 lithium battery from various brands. And here's the various brands for Panasonic, Samsung, EVE, and Sony, and their type of 18650 batteries, and charge and discharge rate, and their operating temperature. As we can see, most of their operating temperature are between minus 20 degrees Celsius to 60 degrees Celsius. So we should control our 18650 lithium battery at this temperature range. And the heat generated by single lithium battery for 1C discharge is about 1 watt, and for 2C discharge is about 2 watts. And the C here means the C rate. The C rate definition is an hour over charge or discharge hours. For example,
fully discharged in half an hour. The C rate is an hour over 0.5. It means half an hour. So the C rate is 2. So fully discharged in half an hour, the C rate is 2. And due to a need for fast charging and discharging, this is necessary to control our temperature between -20 to 60 degrees Celsius for lithium battery. And this report aims to solve the issue of the complex flow in the middle section of air cooling. And so we inserted thermosiphon in the lithium battery module while utilizing air cooling to transfer heat from the lithium battery module and decrease the pressure drop. Here shows the battery module with thermosiphon included 6 thermosiphon and 7 batteries, and we will talk it later. And for two-phase closed thermosiphon, it's also known as weakly sealed pipe. It's a two-phase passive heat transfer device. It has lower cost than heat pipe, and it mainly uses the full phase change to transfer heat from the evaporator section to the condenser section, and then use gravity to make the liquid flow back. Julie et al. Draw a picture about the working principle of thermosiphon. As we can see, first, the liquid deposited in the evaporator section, and when the heat input, it becomes vapor and flow to the condenser section and condense to liquid and use gravity flow back to the evaporator section and finish a cycle. And for micro heat pipe, Moon et al. Doing an experiment for the micro heat pipe. And micro heat pipe used to change the outside shape of thermosiphon to increase the capillarity force. As we can see here, the left-hand side picture, they change to the curved rectangular shape, and the right-hand side picture, they change to curved triangular shape. And use micro heat pipe can also make good contact with lithium batteries. And here's my test section. First, I test the single thermosiphon to find the best filling ratio and use it into my battery module. And here's my thermosiphon. The total length is 135 millimeter. And for my evaporator cross section, I change it into curved triangular shape to insert it into my battery module. And for my condenser section, I compress it into rectangular type to decrease the pressure drop. And for each section, I measure 3 temperature points and to calculate the thermal resistance. And for my module test section for my module, it has 2 types. One type is module with thermosiphon, another is module without thermosiphon. And we can see the module with thermosiphon, they have 6 thermosiphon and inserted into 7 aluminum shell with heating wire to simulate the 18650 lithium batteries. As we can see, we inserted 6 thermosiphon into our 7 aluminum shell with heating wire. And the module without thermosiphon, we only have 7 aluminum shell with heating wire here. And I measure every battery temperature. And for the side view of my module, the module with thermosiphon, the air only flows through the condenser section of the thermosiphon. But for the module without thermosiphon, I put the whole module into our experiment system. And for my experiment system is a wind tunnel system. It included a blower in the left-hand side to inhale the air from the right-hand side here. And I put the test section here, and the inlet and outlet test section has thermocouple to measure the inlet and outlet temperature, and the differential pressure transmitter to measure the pressure drop when the air flows through the test section. And the left-hand side has a nozzle and differential pressure transmitter to measure our flow rate, and the thermocouple to measure the air property. And here's the test result for the single thermosiphon. The filling ratio definition is volume of water over volume of evaporator section times 100%, and the thermal resistance definition is average evaporator section temperature minus average condenser section temperature over heat input. As we can see, the vertical axis is thermal resistance and the horizontal axis is heat input. We can focusing on the blue one here, and the 54% filling ratio has the lowest thermal resistance. And the right-hand side, I change into filling ratio with thermal resistance. We can easily see the 54% has the lowest thermal resistance. It's because when the filling ratio below 54%, the partial dry out happen in the evaporator section, so the thermal resistance might be higher. And here's the module test. When we testing the module, we are focusing on the maximum temperature of batteries and the temperature difference of each battery. The left-hand side picture shows the maximum temperature of batteries. The vertical axis is maximum battery temperature, and the horizontal axis is heat input. The blue one here is a module with thermosiphon, and the red one here is module without thermosiphon. As we can see, our target is control the temperature below 60 degrees Celsius. When we use thermosiphon, we can only control it below 60 degrees Celsius by 3.1 watt per battery. But when we not use thermosiphon, we can control it every single watt. But for the temperature difference of each battery, the vertical axis is maximum battery temperature difference, and the horizontal axis is heat input. The blue one also module with thermosiphon, and the red one is module without thermosiphon. We can see when we insert thermosiphon into our battery module, we can decrease our battery temperature difference. And this is my test result for my pressure drop. And the vertical axis is pressure drop, and the horizontal axis is frontal air velocity. The blue one also module with thermosiphon, and the red one is module without thermosiphon. As we can see, when we insert the thermosiphon into our battery module, we can decrease the pressure drop into 11 pa. And when we doesn't use thermosiphon, it's about 123 pa. And so when we insert thermosiphon, we can decrease it about 11 times lower. And here's my summary. The best fitting ratio of single thermosiphon is about 54%, and the temperature difference of module with thermosiphon is smaller than module without thermosiphon, but the battery temperature is higher. And use a thermosiphon in battery module can decrease pressure drop about 11 times lower. And this is my report. Thanks for your listening.
Thank you. So, do you have any questions? So, okay. So, thank you for your presentation.
Thank you.
And then the time is 10:42. So, next is break time. So,
Thank you for section 1 speaker and chairs. So we will take a short break until 11 o'clock, and please have the tea outside and the dessert outside. Professor Shen will want to introduce himself to everybody. So please wait a little bit.
Yeah, I just want to say, like, I'm happy to be here, but it's a shame I couldn't be here physically. That's all. Yeah, can you hear my voice? All right. I just want to say, like, I'm very happy to be here, but it's unfortunately I couldn't be here, like, physically. It's I was looking forward to this trip, but for reasons you know, like we couldn't enter the country, so that's it. I'm just I hope you guys will enjoy Taiwan, and hopefully we can meet each other next year in Tsukuba. That's it. Thank you very much.
Thanks, Professor Shen's introductions. And let's take a break until 11 o'clock. And please have tea outside. Okay. The section 2 will start at now until 11:45, and we will take a picture before lunch. So let's welcome the section 2 chair, Fangdoni Utomo.
Thank you. Good morning, everybody, ladies and gentlemen. My name is Furandoni Utomo. 私の名前はフランドニです。インドネシアから来ました。For this session two, I would like to introduce the first speaker. It will be from University of Tsukuba, from the Department of Department of Engineering, Mechanic, and Energy. Mr. Ken Sukuhara, with the topic development of deep neural network-based rapid analysis of thermographic visualization of bubble behavior in nuclear boiling. Please welcome Mr. Ken Sukuhara.
Okay. Thank you for your introduction. I'm Ken Kahara, from University of Tsukuba, Japan. My title is Development of Deep Neural Network-Based Rapid Analysis of Some Graphic Visualization of Bubble Behavior in Nuclear Boiling. Then first about the research background. As you know, boiling heat transfer is highly efficient. So in many industrial fields, boiling is applied as, for example, like two-phase immersion cooling, computer cooling, or so nuclear power plant, and so on. Then boiling so improving boiling heat transfer efficient. So we want to create boiling heat transfer mechanism. And this is the tree. This tree is a rough concept of boiling heat transfer, and we focused on latent heat, especially a microlayer evaporation. Sorry, which this. So okay, and so so latent heat is transported by a temperature bubble, but so bubble flow is rapid and mass. So so observation is difficult. Then so Tanaka conducted observation from vertical direction, and he used like this device, and so IR high-speed camera captured his surface, and low temperature, it means microlayer evaporation. So this method can detect microlayer behavior, but image data is so huge that high accuracy analysis demands large costs. So analysis temperature data with machine learning is better. So we thought. Then, so as a first step, this research conducted analysis of heat transfer coefficient distribution, and our objective is to clarify bubble heat transfer, like growth and temperature mechanisms, and develop the analytical method using some graphic images in nuclear boiling. Then, so approach is two steps. First is to measure temperature distribution of boiling heat transfer and obtain bubble parameter. And second step is to analyze temperature data with machine learning to clarify bubble behavior. Then this is heat transfer coefficient distribution. It is made from temperature distribution based on three-dimensional heat transfer equation. So this is fixed position of bubble heat surface by artificial nucleoside, and this site, so bubble generate and grows finally temperature. The red region is a high region, high coefficient, which means so microarea exists. And so we detect so red region and observe bubble behavior. Then next is machine learning. So I used machine learning for bubble detection and classification. I adapted convolutional neural network CNN. So it can judge and classify microarea exists or not, and so I'm training the distribution to like this window and input. So output is a classification. Then concretely, the classification is three types. So notice, please notice, so central center window, and this is not red, so microarea does not exist. And second is red circle, and this is microarea. And this is third is so like a ring. Center hole is a dry patch. So I use machine learning and classify three types. And growth of microarea is so it is important to capture time series information. And then so at first, so nothing, and generate microarea and growing up a microarea. And so I improving my machine learning, so use time series information. And this is criterion bubble behavior. So after classification, I determine bubble generation and departure. And this is the generation definition, and this is departure definition. And so from this definition, obtain bubble period maximum size, because so we can trace each bubble so growing. Then so these two parameters so is used for this equation, and this equation is a latent heat flux equation. And so the classification accuracy, and I used two models of machine learning, CNN and convolutional LSTM. Right graph is accuracy, and horizontal axis is mass and number of frames. It means the time information quantity for input. So, for example, one is single input, and two is combined two frames input, and then compare two or three input is high accuracy, and the single input, and this means time series information is important for machine learning. And after classification, analysis the result. And this graph histogram, and left one, green histogram means the bubble growth period, and brown orange graph is maximum bubble radius, and I fitted this equation and calculate expected value. Then calculation, latent heat using this two parameter. So this equation, bubble generator frequency and departure diameter is unknown. So this following this equation, I calculated, and the green one is result of my research. Ratio of latent heat. Overall equation is for 0.4 bigger, and the ratio is 0.430. And yellow is Yajima research. This is calculation each pixel heat flux in microlayer region. Then we think yellow method is high accuracy. So I want to decrease the gap between two results, but about 10%, 10-point gap. So okay, then this is conclusion. Then I use convolutional neural network, then it enable a discrimination between microlayer and the dry patch from heat transfer coefficient distribution with about 80% accuracy. And the accuracy was improved by incorporating LST. So the second machine learning model, that feedback information from the previous frame. And last, the bubble release frequency is considered to have log normal distribution, and expected value can be used to calculate the ratio of latent heat in boring heat transfer. That's all. Thank you.
Thank you for your presentation, Mr. Arkin. Is there any question from the audience? Okay, sure.
So thanks for your presentation. I have just two questions. One is that you use the machine learning, right? So how many images you just put in input for your analysis? And the second is that I'm not very sure about how do you calculate the bubble departure diameter and the frequency, because they are 3D, right? Have you validated with the experiment or just an analysis from the image? Okay, thank you.
Okay, thank you. And my first question is, I use all data is 5,700 data for learning, and the 10% data, about 570. Second, sorry, one more. So second question.
The second question is that I'm not sure that how can you calculate the bubble departure diameter and the frequency, because that have you validated with the experiment or just analysis from the image, because it's a 3D, right? The 3D behavior. Yeah.
Okay. So so from this definition, so we can obtain the number of generation bubble. So I use the data. So data scale is about 1 second, and so from 1 second, so how many generate, and calculate a frequency.
Other feedback, sir? Any other feedback? No? Okay, that's pretty interesting. Any other question from the audience? Actually, I'm just curious. So you have 700 data.
Yeah.
And how about the ratio for your training and testing data?
Yes. So by 100. So
I mean, the ratio between the training and testing
yes.
data.
Training. So I love it. So
How much is the ratio? I mean, 80-20 or 90-10?
90. So
The ratio.
ratio. Accuracy.
No. The ratio between the training and testing
Okay.
data.
So the train and and analyze, so 9:1. So ratio.
Oh, 90% for training and then 10% for testing.
Yes.
Oh, okay. Okay, thank you. This is a pretty interesting topic. So please thank again for Mr. Ken for the very awesome presentation.
Thank you.
Okay, sorry. Okay, for the next speaker will be Miss Fumi Koshi from University of Tsukuba, with the topic heat transfer near the critical heat flux for forced flow boiling in the circular tube. Please welcome Mr. Fumi Koshi. I apologize, Miss.
Thank you for introduction. I'm Fumi Koshie. I'm second year master's student of the University of Tsukuba. And today I'm talking about heat transfer near the critical heat flux for forced flow boiling in the circular tube. Yes. Yeah. Recently in space, the amount of exhaust heat has been increasing. So there are serious heat treatment problems. For example, this is due to an increase in amount of information and heat transport distance and spacecraft capacity. On the space station, the type of cooling with liquid single-phase flow. However, the thermal problem will be more serious in future. So forced flow boiling is forecast, which is highly effect and large heat removal capacity. It is also have the following like advantages. As shown in this figure, the system is looped. And here, the liquid boil as it draws heat from heat surface. And in short, my research is next generation cooling system for space. However, there are few examples of adoption of cooling system using forceful boiling. And it is necessary to solve the problem for particular application under microgravity. So therefore, the goal of my study is improve cooling performance under gravity environment, and includes critical heat flux is required. And increase the critical heat flux would improve the cooling performance. In this experiment, my object is understanding the impact of each parameter of CHF. Today, talk about its parameter is mass flow rate. In fact, some experiments have been conducted to obtain basic data. This is because there is not enough basic data on boiling under microgravity. My experiment used the same refrigerant as the TPF project. The experimental apparatus look like this. It's a loop system, and the pump controls the flow. And look at this. This is a test section, and which is assumed to adjust the heat surface. And this, instead of heat surface, heat source, a heater is round, like this. And in this test section, 10 thermocouples are installed from the inlet side to outlet side. And this is the preheater in front of the test section, and to unify the convection of the refrigerant flowing into the test section. And the experiment used the refrigerant called perfluorohexane, which has a lower boiling point than water. And this is the same as FC72. And in this experiment, set up the temperature is 10 Kelvin, the boiling point at the test section. And this section explains why focus CHF. The internal field tend to be hotter on the outlet side of the pipe. There's two reasons. First, the temperature is higher on the outlet side because more contact with the heater. Second, bubbles created on the inlet side interfere with the heat transfer on the wall at the outlet side. So with these conditions in mind, it is necessary to pay attention to create critical heat flux on the outlet side. And experimental conditions are shown in this table. A mass flow rate is 100, 200, and 300. The boiling point of the refrigerant is 57.1 degree, and subcool factor was 10 Kelvin. It means that liquid entering the test section sets 47 degree. And local heat transfer coefficient was calculated using this method. And local mean the heat transfer coefficient was calculated for each thermocouples positive in the test section. And flow temperature and wall surface temperature was taken, and wall heat flux was determined from the amount of heat of the heater and the heat loss. The heat loss is in the area direction and tube direction of the tube. As a result, I'll show two things. First, I'll explain temperature variation of the test section. I'll discuss the temperature variation of some couple into the test section. This data is at mass flow rate of 100. The horizontal particle application in mind, it shows how change occurs as the amount of heat is increasing before the temperature has fluid stabilized. Since it is said that 20 minutes is needed for the temperature to completely stay stabilized. The condition is every 2 minutes in the abrupt temperature change. The temperature change in the test tube as shown like this. One is inlet side and 10 is outlet side. And here that when the large amount of heat is added, boiling occurs on the temperature raised rapidly, but the temperature on the surface on the tube decrease as the heat is transferred to the refrigerant and boiling occurs. And as more heat is added, the temperature is raised. As shown in this graph, the temperature is higher from outlet side, especially outlet side. At the beginning, it doesn't change significantly because the tube can be cooled. But as the amount of heat added includes cooling, is no longer positive and is no longer possible and it continues late. This would cause a durability problem for cooling used in space. Therefore, it is necessary to understand where such temperature raise start. And second, I talk about calculate of heat transfer coefficient. I've discussed the local heat transfer coefficient, and this data is mass flow rate of 300. The horizontal axis is the elapsed time as before. This is a result of local heat transfer coefficient using the surface temperature data. And this area is boiling occurs here, and the heat transfer coefficient increases as the boiling were more active. The higher heat transfer coefficient, the more heat equipment can transfer to the refrigerant, and thus the higher the cooling performance. And in this graph, the heat transfer coefficient on outlet side rapidly decreasing. Especially at 10, the temperature tend to be higher, so CHF is reached sooner. And this point, outlet side 10 reaches critical heat flux. This graph plot input heat and the point where CHF is reached. As the mass flow is increased, input heat also increases. And this plot shows that there is a linear relationship. Here's my summary. My object is understanding the impact of each parameter of CHF, and especially this time parameter is mass flow rate. And I took first temperature variation of the test section. It showed that tube outlet side hottest and temperature increasing rapidly from the certain point. And this certain point is critical heat flux. Yes. And second, the calculus of heat transfer coefficient and show that estimation the heat transfer coefficient facilitates the determination of the critical heat flux. And before CHF, boiling includes heat transfer coefficient. And my future plan, rapid in experiment, rapid increase the heat value in hot load application and increase mass flow rate when CHF is reached. Thank you for your kind attention.
Thank you for the presentation. Any question from the audience? No question? Okay.
Your test results before heat flux. Can you move to the temperature variation in the previous page? The previous one. Okay, this. So that's the temperature at the later point is higher than the earlier point, right?
Yes,
This
yes.
means because you use the constant heat flux, right? So the constant heat flux, this means the heat transfer coefficient at the later point is lower than at the earlier point. Is this correct?
Oh,
okay.
sorry,
You tested its constant heat flux.
Yes.
Right? The same heat flux through the entire tube.
Yes,
right?
yes.
So the surface temperature higher means the heat transfer coefficient is lower.
Yes,
Is
yes,
this
yes,
correct? Yeah,
yes.
okay. But I wonder that before heat flux inside the tube.
In tube?
In tube, yeah. It's the annual.
Yes.
It's annual flow, right?
Yes. In my opinion, the tube more the bubble is more more bubble on the wall. So it good. It is not good for the cooling system.
Not cooling,
Yes.
cooling system.
Yes.
Yes. What my question is the propellant transfer from the bubble flow and then finally to the annular flow. And annular flow means is the film on the wall, right?
Yes. Yes.
Yeah.
Yeah.
Why it is film? The film thickness is getting thinner from the inlet. So the heat transfer coefficient before the critical heat flux should be higher at the outlet before
Yes.
critical heat flux. But I find that from this figure, you find that before the critical heat flux at about 800 seconds before it one.
Yes.
But it's always the temperature at the inlet part is lower than the outlet part. But this is not the same as the propellant we adjust. We think it should be at higher heat transfer coefficient for the lower film thickness.
Yes. Thank you. Thank you.
Thank you. Pretty interesting. Okay, thank you again for your presentation, Miss Fumi Koshi. Give applause for Miss Fumi. Thank you. For the next speaker and the last speaker for this session is Mr. Watanabe Nozomi from University of Tsukuba. With the title of the presentation is Characteristic of Carbon Dioxide Disruption from Ionic Liquid by a Hollow Fiber Membrane Contractor. Mr. Watanabe.
Thank you, my introduction. Hi, I'm Nozomi Watanabe from University of Tsukuba. Today, I'm going to talk about carbon dioxide absorption and disruption in. Okay. Okay. Thank you. Today, I'm going to talk about carbon dioxide absorption and disruption in ionic liquid by fluorofiber membrane. My supervisor is Professor Matsumoto. He is belong to JAXA. JAXA is Japan Aerospace Exploration Agency, and I research at JAXA. First of all, I'm going to talk about research background. Spacecraft must have a carbon dioxide removal system because people emit CO2. Currently, ISS have some carbon dioxide removal system, and the famous system is a CDRA. CDRA is a used solid zeolite, uh, solid zeolite, and for absorptant. But CDRA has some problem. For example, after repeated use, powder begin to appear due to solid zeolite, and then pipe is clogged. Other example is increased size due to absorption performance. Next, what is the ionic liquids? First property, ionic liquids are salt in the liquid state, so no powderization. The second property, ionic liquids are composed of anion and cation, so there are a lot of combination, so it is easy to choose the appropriate liquids. For example, if we choose the high efficiency liquids, the efficient can be power saving. Equipment is power saving. So my research, I selected the ionic liquid is 1-butyl-3-methyl imidazolinium acetate. So I call the BMIMAC. This liquid feature is considered to have a little impact on the human body and response power fluctuation due to less viscosity increase in CO2 absorption. This graph is the BMIC isotope. The horizon axis is the CO2 pressure, and the vertical axis is the weight of CO2 fraction. In short, from this graph, when CO2 absorption is low temperature and high pressure, when disruption is high temperature and low pressure, so it can be used in rotation for repeated use. The next previous study, one of the NASA study is carbon dioxide absorption experiment using fluorofiber membranes. These contactors merit separate the liquid and gas and large contactor surface property. However, power saving and high efficiency, it is necessary to consider absorption and disruption efficiency. Therefore, my research object characterization the influence of parameter on the absorption and disruption of carbon dioxide absorbed in ionic liquid by fluorofiber membranes contactor. There are two approaches. As previously I said, it is needed to alternate absorption with disruption. So I talk first about absorption experiment. The first step is study the efficiency of absorption as a parameter of air flow rate and ionic liquid flow rate. The second step is the study method to maintain a content amount of carbon dioxide absorbed for disruption experiment. This is my experimental equipment schematic. This equipment has a two airflow and ionic liquid flow. The green line is the ionic liquid flow. And the purple is the airflow. When absorbed experiment, the air from the gas cylinder through to the CO2 probe and the flow fiber contactors and CO2 probe and the flow meter and outside. But when we try to disruption experiment, this stopper is used to block the airflow path, and then this area is the vacuum area using the vacuum pump and release through CO2 probe and the flow meter and outside. This is the absorption experiment result. The horizon axis is the time and the vertical axis is the CO2 concentration. The blue line is the entrance concentration. So this probe values, and the orange line is the exit concentration. So entrance is higher concentration than exit because of the entrance before absorption. As you can see, the airflow rate was examined to see if there was an optimized airflow rate by changing the airflow rate. However, since the airflow rate is varied and difficult to discuss, so when I calculate the air absorption rate, absorption rate was the mass flow rate of carbon dioxide into liquids. Calculation this formula. This is a graph plotting the absorption rate. Horizontal axis is the time and the vertical axis is the absorption rate. As you can see, absorption rate getting down. Also, absorption efficiency is stable in spite of small changes in airflow rate. However, high pressure change may occur depending on the airflow rate, causing changing absorption efficiency. So we talk about one absorption experiment. So next, I'm going to talk about the second disruption experiment. The experimentation, we researched the effect of temperature change and vacuum levels. The disruption experimental condition is 2% absorbed per ionic liquid's mass. This is very close to the limit. This graph is a disruption experimental result. According to this graph, out of carbon dioxide could be dissolved by vacuum without temperature change. This liquid may be able to reduce the temperature rise. However, the limit of our measuring device is 3%. So as soon as the environment is ready, we would like to conduct the experiment. So this is my conclusion. My research objective characterize the influence of parameters on the absorption and disruption of carbon dioxide absorbed in liquids by pore fiber membranes contactor. From absorption experiment, absorption efficiency is stable in spite of the small change in airflow rate, and pressure change may occur depending on the airflow rate. From disruption experiment, disruption at higher than expected carbon dioxide concentration and possible temperature change can be minimized. So this is my future plan. Thank you for listening.
Thank you, Mr. Nozumi, for the presentation. Is there any question?
So thank you for your interesting experiment. And this is a very interesting topic that you want to do the high efficient carbon dioxide removal system, right, in the spacecraft. So your carbon dioxide is maybe it's from the human, right? The human behavior in the spacecraft. So I don't know the humans the CO2 ppm is what the value, and is your experiment the CO2 ppm is selected from the human behavior in the spacecraft? Because you can see your experiment that only 2 days, right? The time hour, it may be your slide, the experiment. Yeah, this one only 2 days, right? So after 2 days they will change the liquid or something else.
Yeah, NASA's research is half of the year. But that is no problem. So this research is not long period. My research is the change the airflow rate. So how to more high efficiency. So my object is not.
Okay, thank you. Any other question?
Oh, okay. Very nice talk. My question is about the ionic liquid. Did you know or did you have the data of the cycle, the lifetime? For example, maybe 100 of cycle, then the absorption rate tend to decrease. So what is the cycle life? Do you have this data?
Data because this liquid is in the future we want to use the absorption and disruption at the same time. So this equipment is only experiment. So if we want to use the in the ISS, maybe and
because you are working in this circle, right?
Yeah,
so that
yeah,
means
but-
that you have the cycle lifetime. Or you need to repress the fresh ionic to keep the same absorption rate.
Sorry, I don't know, but in the future, this is the only one way to absorption or disruption. But in the future, we try to hear and four fiber contactors, and this contactor is absorbed, and this contactor is disrupted. So we use this at the same time, disruption and absorption.
Okay. And the second question is about what is the disruption rate? You only have the data for absorption, but actually for real application, the disruption rate is more important.
Yeah, now disruption rate is so sorry, I do not calculate, but 0.6 milliliter per minute. So now I can't calculate now. Sorry.
So that means it's not fully dissolved. That's on this condition. Partially dissolved.
Sorry, I can.
I mean, the fully disruption
Yeah.
normally require higher temperature, right? I just mentioned about that this disruption rate is lower, right? So that is due to what reason?
We expected more high efficiency. So if change the high temperature, the more out of
Power.
CO2,
Power
yeah,
consumption.
CO2 disruption.
Okay, thank you.
Thank you for your presentation, Mr. Nozomi. We give another applause for Mr. Nozomi. And this is the end. This is the end of the session 2. That we will have a lunch time. We'll give it back to Mr. Chung.
Let's go outside to take a group photo first, and they go back here to take the lunch box for our lunchtime. We will take picture in the lobby of the mechanical engineering building. Okay. Hello, everyone. Let's start the section 3. The section 3 will begin in 1:30 to 2:50. Let's welcome the section 3 chair, Fumi Koshie. Please applaud for him.
I'm a chairperson for this session, Fumiko Shie from University of Tsukuba. I'd like to welcome our first speaker to the stage. From National Central University, Mr. Aditya Fija Bekti. Please come here.
Yes. Good afternoon, everyone. My name is Aditya. I'm from Energy Technology Laboratory under the supervision of Professor Cheng Chongren. Today, I would like to present one of my research study about the thermodynamic assessment of protonic ceramic fuel cell, gas turbine, organic Rankine cycle, hybrid system with the external octane steam reforming. And this is my today's presentation outline. I would like to start from the background, then methodology, system configuration, result and discussion, and the last one is the conclusion. So for my research background, we can see in the left-hand side figure, this is the figure from Institute of Combustion Technology 2020. Here, the solid oxide fuel cell and gas turbine hybrid system is the highest electrical efficiency for the hybrid system so far. And this electrical efficiency still can be optimized by employing the additional power generation unit like organic Rankine cycle system. And why I study the proton conducting SOFC in the left-hand side figure. This is the experimental data from Mangni et al. 2009. In this experimental data, they explain that the proton conducting solid oxide fuel cell has the higher cell potential or cell voltage than oxygen conducting solid oxide fuel cell at the same range of current density. That's why in my study, I analyze about the SOFC GTORC using the proton conducting fuel cell. And this is my methodology. I would like to take a note that the most important thing in order to perform the fuel cell system analysis is how to build or create the good polarization model for our system. And because my system, the main power drive is a solid oxide fuel cell, in my study, I use the NIO-BCZY as the anode fuel cell material, BCZY as the electrolyte, and LSCF-BCZY as the cathode material. And for this study, MATLAB was employed for the polarization modeling, and for the system modeling, we use MATLAB Simulink and Thermolib software. For fuel cell itself, I use the anode support fuel cell type with the operating condition at 5 bar pressure, 700 degrees Celsius cell temperature, and for the anode electrolyte and cathode thickness, are 30, 15, and 18 micrometer respectively. And in the left-hand side figure, this is the IV curve or polarization data validated using this following paper by Chen et al. 2022. It range temperature 500, 600, and 700 degrees Celsius. And the cell voltage in this figure was evaluated by calculating the open circuit voltage of the fuel cell minus the overall polarization losses, including the activation, ohmic, and concentration. So finally, we can say that the IV curve validation is perfectly matched and acceptable. And this is my system configuration because my research focus on the system modeling. So let me explain in briefly the system as the initial system, at the initial process. I mean, at the anode side, we can see for the red line, the octane fuel was compressed using the fuel compressor, and at the blue line, the water pump by the water pump, and then for the green line, the combination of fuel and H2O was preheated to satisfy the octane reforming temperature at the level of 600 degrees Celsius. And the syngas production happened inside the octane steam reformer reactor. And then the purple line, the hydrogen-rich gas delivered to the anode PCFC to generate the power. And also for the cathode side, the air was compressed and preheat to satisfy the temperature requirement for the fuel cell cathode inlet. And then the gas output from the anode and cathode was burned inside the combustor to rise up the overall system temperature and also trigger the expansion process inside the micro gas turbine here. That's why the system called the PCFC, gas turbine, and ORC system. And then from this configuration, system configuration, the 30% heat output from the micro gas turbine deliver as the heat source from for the cathode preheater before entering the cathode inlet, and then the rest 70% of heat comes from the micro gas turbine was used as the heat resource for the fuel preheater and also octane steam reformer. And in this system configuration, the cooling PCFC utilized the heat output from the steam reformer and cathode preheater. And the final residual heat comes from the splitter 4, and cooling PCFC was sent to the ORC system to generate the additional power using the organic Rankine cycle. And this is the detailed parameter used for the system modeling. I use the heat exchanger effectiveness value of 90% based on this following paper, and also for the octane steam reforming reaction following this formula in order to optimize the syngas production. And this is the result and discussion section. This is the exergy flow data of proton ceramic fuel cell GT-ORC system. Based on this exergy flow data, the total exergy input is equal to 233 kilowatt, and the total exergy destruction is equal to 74 kilowatt. And we can see here the total exergy destruction mostly comes from the PCFC component and also the combustor, where the chemical reaction occur. So for this configuration, the exergy efficiency equal to 68%. And then we notice that due to the high temperature requirement for the octane steam reformer, so that this reformer can convert the fuel, in this case octane, into the hydrogen-rich gas, we need equal to 50 kilowatt of exergy flow. And finally, we have 41 kilowatt exergy flow to generate the additional power over the ORC system. And we can see the ORC power generation is equal to around 17 kilowatt. And this is the exergy flow data for the PCFC GT CHP system. And this data is exactly same as the previous, but in here, the ORC system has replaced by the heat recovery steam generator in order to generate the steam at the temperature of 80 degrees Celsius, and the heat recovery steam generator efficiency up to 63%. And this is the final result in my presentation. So this is the comparison data of the energy efficiency and then exergy efficiency. I found that the CHP system can improve the total energy efficiency by approximately 5%. And this is my conclusion. I have 3 conclusions so far. So the first one, the proposed PCFC GT-ORC system fueled by octane produce an overall energy efficiency up to 69.98%. And then the second one, the CHP system has proven to enhance the overall system efficiency by up to 5%. And then in addition, the proposed system has the flexibility to use the ORC and CHP based on the demand for electrical power and heat. Yeah, thank you so much for your attention.
Mr. Aditya, thank you for very much for interesting presentation. Now let's open questions and comments from the audience. Do you have any question? Okay, then may I ask a question? How about the 5% is high or low, and in the future is more high percent in your study?
Yes, thank you very much for this good question. So this 5% higher by utilizing the CHP system still can be optimized by using the low temperature reforming fuel. In my case, I use the octane, but nowadays we know that a lot of fuel that have low reforming temperature, such as ammonia, methanol, and even ethanol. Yes, and I'm working on it for now. Yeah.
Any other question?
So compared to this figure, so how much efficiency improvement you get? Thank you.
Yeah. Compare with the source data from the Institute of Combustion Technology 2020, my result has similar result, around 70% by using the SOFC GT ORC. Yes, and in my case, I use the octane that have high reforming temperature. Yeah, so we can still optimize the result of this research, and we can surpass this source data.
Thank you for your
Yeah.
presentation. Yeah. Next, thank you so much. Next, I'd like to welcome the second speaker to the stage, and Mr. Jin Shanglin. Come here, please.
Good afternoon, everyone. My topic is advancing in polymer electrolyte membrane fuel cell performance using laser processed nanoporous platinum cobalt catalyst and Neptune casting. Two key challenges in this topic is we seek to reduce amount of platinum group metal in catalyst layer, and we seek to increase the output power density of our proton exchanging membrane fuel cells. Here show the current market price. We can see the platinum is a expensive metal compared to the cobalt. So if we use the platinum to cobalt atomic ratio with 1 to 3, we can reduce the cost of raw material about half. And to our second projective, we need to increase the ORR reaction rate in our cathode. So we use a method to increase the effective triple phase boundary surface area with more adequate electron, proton, and gas transport phase. For the conventional catalyst layer is coating by ink coating process, but it restricts the electron and the gas transport path by the surrounding the ionomer material. So we use the physical vapor deposition method to fabricate the ultra-thin film catalyst layer, shown like this structure. It have a good electron transport and the proton transport from the top from membrane, proton exchange membrane. So in our work, we use pulse laser deposition. It is set in a vacuum chamber, and the high energy density laser will strike on the metal target. This is for the catalyst material and generating a plasma plume. And then the plume will cool down by the background argon gas, then deposit on our substrate. Here show our previous work result. We use the carbon paper with microporous layer, showing SEM image like this, and this figure show the microstructure of our platinum coated carbon paper surface morphology. And to test the fuel cell performance, we fabricate our membrane electrode assembly like this. We selected 2 platinum coated carbon paper with stubber gasket and a commercial proton exchange membrane by hot pressing and get this MEA. then insert this to our single cell. And we found that with lower platinum loading goes by the pulseless deposition, the performance is equivalent to the higher loading platinum using the traditional ink coating process. So in this work, we replace the target in our pulseless deposition system by this alloy, and then combine with the laser continuous wave laser processing. We use the green color laser beam, have a line shape to scanning on our catalyst layer, and we will get a PT rich surface catalyst layer. And the laser parameter should be optimized for get better performance. So we optimize the optimized parameter is at 2.4 watt and 0.35 millimeter per second scan speed. We can get highest mass specific electrochemical specific area. This means have higher activity in the catalyst. And we found that in SEM image, the pristine alloy catalyst will look like this, and the laser scanning processing can alter the microstructure to like this. And we check their nanoparticle size. We found that with optimized the parameter, the nanoparticle size will not enlarge it to be too large to decrease our specific surface area. And then in comparison of our fuel cell performance, we found that with the optimized laser parameter, we can increase the performance of our alloy catalyst greatly. And we compare with the pure platinum catalyst. We found that we can see the green line and the black line. Black line is the platinum with 50 microgram per centimeter square loading of platinum. And it is similar to this alloy case. We can get a higher current density compared to the pure platinum. And we also do the durability test. In the TEM image, you will find that without the laser sintering, the catalyst, alloy catalyst will grow larger in our durability test, but SCWLP1 can keep their nanoparticle size. So in short summary, in this work, the platinum-rich shell catalyst was direct synthesized on the carbon paper by our laser processing, and the durability was enhanced, and the fuel cell performance also enhanced. And then we will face a problem because we use the alloy catalyst. The catalyst there will be thinner, so it will influence to our proton and the gas transport region. So we propose a method by dropcase Nafion on our catalyst layer to direct form a proton exchange membrane and get improved proton transport in the catalyst layer. So we developed a two-dimensional CNC machine to precisely dropcase the Nafion precursor on our substrates and connecting them to a liquid film, then drying, and we can get the Nafion thin film on our sample. And compared to commercial membrane, we stack this sample to MEA just need to with subgasket and then hot pressing. So this Nafion, drop case Nafion will replace the commercial membrane. And then this shows a cross-section view of our membrane electrode. We can control our Nafion membrane by our drop casing Nafion precursor. And for comparable, we use similar thickness to compare their performance. And in detail, this white line is the catalyst layer, and here is the proton exchange membrane, and these two black region is the carbon paper. And so the drop, and the other point is the drop case Nafion membrane should be optimized by the drying temperature of the Nafion precursor and the assembly hot press pressure. This will influence on the charge transfer in catalyst layer, and the thickness will influence to the ohmic resistance. Here is the enlarged cross section. We can see some Nafion will infiltrate into the catalyst layer, but the commercial membrane one did not. And finally, we compare with the different catalyst thickness. The thickness will controlled by the catalyst loading. For the left one is 100 and the right one is 200 microgram per centimeter square. And in the figure, we also compare the commercial membrane and the drop case membrane with varied operating gas pressure, the feeding hydrogen and oxygen pressure. And we can see that with the thinner membrane, thinner catalyst layer, the performance was not quite different to commercial and drop case one. But for the thinner case, the drop case Nafion can greatly improve the performance. So it proves our thesis show our assumption is right. So in conclusion, we developed the drop case method to direct deposit proton exchange membrane on our catalyst layer, and can solve the proton transport limitation of the thinner catalyst layer. And in future, we'll combine the laser processing catalyst layer and this drop case method. This is my work. Thank you.
Yeah, the presentation. And now open the question, comment. Do you have any question?
Okay, so I want to ask two questions. So first, you two variation of the increasing the PT loadings from 50 to 100, and so this will improve. And then so the 100 is the maximums, and the second one is the for the second one is the you change the scan rate, and then you saw some SEM, and then you saw us that you have improved your fuel cell performance. Is that because the porosity change, or what is the phenomena why you have good improvements?
Okay, so
from the SEM. Thank you.
Thank you. For the pattern loading question, this from our previous work, we found that if we further increase the loading for pure pattern, we cannot further increase the current density because there have some proton and gas transport problem in this kind of nanostructure. So in our first part we drop Casnafian. It will solve the proton transport limit. So maybe we use a higher pure pattern loading, we can get a higher performance. And for the this laser processing question, actually in the more detailed TM image, we found that we can get a pattern rich surface to get a better performance. So it quite look like a kosher structure. This is a nanostructure level view, but in this microstructure view, this structure can also be more stable. It has tested by the we can immerse we have tested this sample in the liquid electrolyte. So to test the durability, we get this result with the laser processing. This catalyst can more stable stack at the hands on our substrate. Yes.
Anything else? Okay. Mr. Chen, thank you very much for your wonderful presentation.
Thank you.
I'd like to welcome our third speaker to the stage, Mr. Yu Liang Yu.
Good afternoon, Professor and everyone. My name is Liu Yuwen. The topic of my report today is study on the interaction of shock wave between dual circular cylinder obstacle in supercritical granular flow. This is the content of my report today. I will divide into 4 chapters: introduction, method, result, discussion, and conclusion. And particle is a common substance in our life. They are in this figure. You can see they are the product for pharmaceutical and others in industry, for steel marking in industry, and sand in nature all belong to application of particles. And above land, nature disaster phenomena such as debris flow and snow avalanche. When disaster occurs, they usually have a larger flow range and stronger destructive power. Therefore, it is common to building densified structure to block or divert this granular flow, such as check dams and retaining wall and deflecting dams. And there are different types of defensive structure. And this study, two cylinder obstacle set on the chute to generate 2 shock wave. And the interaction shock wave is observed. The 2 figures are schematic of experimental setup with a dimension of definition of coordinate. I set X as the width direction on the chute, and Y as the flow direction, and Z as the depth direction. The left figure is my experimental equipment, and this table is control parameter table. I fix the gate opening height is 2 centimeter, and the
6 different inclination angle on the chute, and the 4 cylinder spacing. And where is S is mean distance between two obstacles, and where D is the diameter of cylinder. Also, I use the particle materials is silicon sand. And this is data analysis. In order to obtain velocity and depth, a camera record image. The PIV is employing to calculate the velocity field, and the depth field is measured using the laser profiler scanner. And these C image are experimental images at a different time point. And on the right is flow process. In this figure, you can see the flow field is stable flow, nearly 1 second. In this study, analyzed to the flow field at steady state. And this is result of depth. The left figure is variation of the depth in y direction. In this figure, you can see the over depth increase with inclination angle, because there are two factors affecting in the depth. One is penetration effect, will cause the depth to decrease. The other is expansion effect, the depth to increase by collision between particles. And in order to compare the result of group, the right figure is variation of maximum depth with the shielding spacing. I use the linear fitting to represent the trend of change. And you can see different trends. One is the theta below 45 degrees. The maximum depth decrease with S. And the other is when theta is above 50 degrees, the maximum depth increase with S. And there is result of full number. The full number is very important parameter for the fluid flowing in the chute. It can represent the flow properties. When the full number is less than 1, it is subcritical flow, and it's larger than 1, it is supercritical flow. And the left figure is variation of flow number in y direction. Basically, the changes are similar to velocity. And the right figure shows the minimum flow number of all groups. And you can see that only under the condition of 0 point diameter, the flow number will be less than 1. There is the subcritical flow. And the other groups belong to supercritical flow. And that is the result of fluctuation velocity and granular temperature. And the upper left is fluctuation velocity U plan in X direction. The upper right is fluctuation velocity V plan in Y direction. And comparing these two figures, they are mainly distribution in middle, left, and the right side. And the V prime is also distribution around the best obstacle. The lower right is granular temperature field. Its distribution similar to V prime, because the flow field in experiment many flows along the y direction, and the velocity change larger. So the proportion of V prime is greater than U prime. resulting the granular temperature is dominated by V prime. And in this study, V prime is very important. The left figure is variation of V prime in y direction. And you can see the fluctuation is mainly concentrated near the y equal 10 centimeter, and which is also the position where the shock wave start to interact with each other. In order to compare V prime of all groups, I take axis range and the average V prime. The range is between 8 to 12. The right figure is a variation of average fluctuation velocity with cylinder spacing. And I also use the linear fitting to represent the trend of change. And you can see two different trends. One is when theta is below 45 degrees, the average fluctuation velocity decrease with S. And the other is above 50 degrees, it increase with S. And the average temperature and the average granular temperature has the same trend as this figure. And in addition to analyze the quantify the result, and different flow features are also found based on the depth profile. I found the three different flow types. One is the first with a bolted shape, and the second is cone shape, and the last is bracelet shape. The left figure is the phase diagram of all groups, and you can see that the bolted only occur under the condition of 0.5 diameter, and the cone has a large distribution range and can be observed between 1 to 2 diameter. And finally, it is braces, which is mainly distribution in the lower right of the figure. That means the larger S is, the theta, the smaller theta is and easier to observe. In addition, the flow type is related to minima flow number. The minima flow number is less than 1 for the bolted, and between 1 and 1.9 is cone, and larger than 1.9 is braces. This is my conclusion. The shock wave phenomena generated after granular flow impact the obstacle makes the physical qualities such as the depth and the velocity discontinue change. The maximum depth and the average fluctuation velocity and the average granular temperature have the same trend, indicate that the increased fluctuation velocity and granular temperature will cause the granular flow field to become dilute. The expansion behavior of the fluid will further increase the maximum depth. Different flow types are identified from depth profile. It can be found from the phase diagram that flow type is related to minima flow number. And thanks for your attention.
Thank you for your presentation and then this question and comments from the audience. Do you have any question?
Thank you very much for your interesting talk. And I have one question. Sorry if I lose your explanation about the how to measure the depths. I think in slide 10, you show us that. No,
The-
10, please. 10.
Oh.
This Z means the depths, right? Oh, so how to measure this depths values in your experiment? Explain how to measure that.
How to
Measure.
measure?
Yeah, this depths value. Is that the?
I use the laser profile scanner.
Some well, the people. Okay, so okay, it's please move to the 10. Number 10.
Number 10.
The average value or some is that average? I mean the series, right?
Yeah.
Please show the slide 10.
10. Yeah.
The values are to show us the variation over the change of the maybe the angular theta, but these values are average over depths or some. I mean, during your experiment, the depths will be changing in time series, right?
Yeah.
So this value is average, right, in time series, or not?
And you mean is average depth?
Is average.
I maybe is yes.
I see. Okay, so it's sorry, I think where is the values of in your experimental test section? You know, you put the cylinders and sorry, where is the S equal 1D and X equals 0D? I want to know the point of measurement point.
And I
Okay, yeah.
oh Z as the
Yes.
depth direction.
Oh,
Yeah.
And you measure the position of in a right hand, maybe top view, you can point it out that measured that.
And I measure the distance
It's a
between.
cylinder?
Yeah, I start point is this here. And I measure the here.
Okay. Okay. I thank you very much. Yeah, interesting.
Okay.
Thank you for your question. Professor Shen,
Yes. Can you hear my voice?
Yeah.
Okay. Total amateur question here. Like, what's the definition for granular temperature, and how do you measure it?
Do you mean granular temperature?
Yeah. Like, I'm not from this field, so this concept is completely foreign to me. So can you explain to me what is granular temperature?
I do you mean calculate the granular temperature?
Yeah.
Yeah. I use the U prime plus T and V prime plus B, and he have a formula, and
Right.
U prime square add V prime square divided by 2.
I see. And like what kind of physical meaning does this quantity have? If you have very high granular temperature, what does it mean?
And that means is the higher the particle temperature, the more the particle behavior the like a liquid or gas.
I see. I see. Thank you very much.
Thank you.
Thank you for your question. Do you have any question? Okay. Mr. Liu, thank you for your presentation. Is it the time to coffee and tea break for 30 minutes? Yeah. 24 minutes. Yes. From now. Thank you.
Excuse me, Mr. Eugene.
Can you hear me? Can you help me to share your screen? You can try to share your screen, your PPT. Actually, you can talk, you can speak, but your microphone is still in mute. You can unmute it first. Okay, we get your share screen. But I think you get a not this screen. I mean, you can end your sharing screen and then choose the other.
So is it okay now?
Let's see. We still haven't got your PPT, your screen.
Can you see my screen now? Is it
Not
okay
this
now?
one. Oh yeah. Okay. We got it.
Okay.
Okay. How about the others? Is there any problem? The other speaker, Mr. Chow, maybe?
So you mean I can stop now? Can I stop sharing?
Maybe it's better just let it share like this
Okay.
because it will start maybe around 10 minutes.
Okay, fine.
Okay, it's yeah. All right. Thank you, Mr. Eugene.
Okay. Thank you. I'm okay.
Mu Tingxie. Let's welcome the chair of the section 4.
Hello everyone, my name is Mu Tingxie, and this is the next session, and I'm the lead session session chair. And to remind each presenter, the raining bill will rain in 10 minutes one times and 12 minutes twice times. And now the first speaker is the Gatete Eugene, and his topic is improvement of the accuracy of PIV measurement of flow in a droplet. Let's welcome him.
Thank you for introduction. I'm Gatete Eugene from Thermofluid Controlled and Measurement Lab at the University of Tsukuba. So as you said, my presentation today is on the improvement of accuracy of PIV measurement of flow field in a arrested droplet. So as an introduction, a droplet is a small column of a liquid bounded by a free surface. Then various methods such as suspended, seized, and levitated can be utilized for droplet analysis in showing internal flow, field, curvature distortion, evaluating parameter affecting internal flow measurement. However, after imaging through a visual system, too many type of optical distortion such as radio, tangential distortion occur. Then a droplet is widely used in several scientific and engineering applications where we see its involvement in power plant, microfluidic biological manipulation, combustion engine, humidity control, water harvesting, and the HVAC system technology, and also in a cooling system. So therefore, a study of droplet helps to increase the efficiency of their usage in these areas. Then one method to analyze the droplet is acoustic method. And in this method, a droplet is normally controlled by acoustic pressure, and the pressure distribution is created by acoustic sound wave in a test section. And droplet of millimeter scale can be located near the node of the sound pressure. And here, internal flow and the external flow can be visualized. In recent years, containerless processing, such as levitation method, has attracted much attention, where three-dimensional transportation technology of particle has been reported by ultrasonic phase array. In this way, acoustic levitation method enables levitation and transport of droplet without a container. Then by using this method, we can avoid problems such as caused by container wall, such as heterogeneous nucleation contamination, absorption, adoption of solution. And it's also expected to be used in applied to material production in analytical chemistry and also drug discovery. Here are some examples of levitation technology, where these methods have been applied for fields such as physical property measurement and new material generation. Then in recent years, I've seen these examples, such blood analysis and levitation of living animal. They attempt to levitate technology, levitation technology to biotechnology, and also to analytical chemistry and drug discovery has been visualized. So, but the analysis also for this method are always disturbed by the distortion. So then various methods were also used to collect this distortion, and one of them is a ray tracing method, which was provided by Kangler et al. And the Meinler et al. This method normally can be benefit from quantitative visualization and also velocity field measurement. Normally, the problem here is that the acquisition of this data as normally traveled by the fraction of light at the droplet surface. Then their method, they use two methods, MMI and VMMI. And when the curvature distortion was applied to the position of vortex, the magnitude and magnitude of velocity vector, it was found that the vortex center and velocity vector reduced toward the center, and also the processing result at almost the same result for the ethanol concentration. However, there is still lack of experimental knowledge of fluid curvature distortion collection and stock lay. Then hence, there is the curvature distortion of flow structure inside a levitated droplet need to be visualized and collected and to collect the flow structure inside and outside of the droplet. So then that's why we come up with our main objective, which normally intend to reduce the curvature distortion by improving the accuracy of velocity field measurement of a levitated droplet. Then the above method can be achieved via this following specific objective. And also this method has been used where the PIV method have been used to visualize the internal flow velocity vector, and also PFV contract software were used to analyze the internal flow of curvature distortion. And the Python was also used to investigate the curvature distortion. So this is our experimental setup and condition used where a droplet is levitated at the mid area between two refractor, and the internal flow phenomena can be observed and analyzed. Then in this case, to visualize the internal flow structure of a droplet, fluorescence particles are mixed up with a test fluid as tracer particle for internal flow measurement. And also a laser is related to them to measure the flow in a horizontal cross-section of a levitated droplet. Then in the image here, you can see as a part of our result, the image 1A to 2D illustrates two-dimensional velocity vector distribution from side view for different water glycerol concentration. Then with refractive index, the complex internal flow was observed in the fluid in the fluid droplet. Then comparing the A and D, it can be seen that the water droplet, the complex internal flow was observed, while in a glycerol droplet, the rotating motion was observed like a rigid body. Then the difference here in flow structure could be due to the influence of rotational instability attributed by acoustic stand because of the shift of the droplet axis with a levitator axis. And also this result in a constant direction direction of droplets, which can be seen as single cell circulation in the center, from as can be seen in figure A to C. So therefore, we can say that the curvature distortion affects the internal flow measurement for a levitated droplet by increasing the refractive index. And also, as can be seen in this figure, the water droplet showed the higher velocity with a maximum of 28.7 millimeter, a decrease with time, while the glycerol showed 5.6 millimeter decrease with 5. Then as the aspect ratio is concerned, it can be seen that the droplet, that the flow strongly obstructed the particle images as the aspect ratio increased. Hence, the center part of the droplet can be visible, while the edge cannot properly seen due to curvature distortion as the aspect ratio increase. So therefore, the higher the aspect ratio, the higher the curvature distortion, which leads to invisible tracer particle. So since also the diameter govern the flatness of the droplet, the droplet also decreased by 1.02 to 1.74 with increase of time. And also, the aspect ratio was also decreased by 1.85% to 2.7. So this shows that the curvature distortion of a lifted droplet can be affected by inertial force, by sound pressure, and surface tension. So this is our optical arrangement of photographing of distortion curvature of simulated droplet in acrylic material, where here a simulated droplet was used to visualize the curvature distortion using circular pattern for further reconstruction of calibration method of the image. Then to obtain the calibration parameter value for droplet, the distortion due to curvature to camera pixel, the image processing interface in Python was used to from the top of the droplet was applied. Especially, we are aiming to improve the accuracy of PIV measurement of the flow field inside the droplet. So the material used here are PMMI and PC. So here are the images captured for distortion collection pass using a calibration method based on the blonde distortion method. So then the blonde distortion model based on the calibration from the OpenCV programming tool was used, where image was loaded in Python and it was binarized and the feature was detected, and by applying the mapping function, the calibrated image were obtained, and also both internal and external parameters were determined. Then here are the images before and after distortion, and where you can see that to quantitatively analyze the accuracy of calibration method, the mean reprojective error were founded for all considered the aspect ratios. And it can be seen that the aspect ratio presented the right distortion as shown in the accuracy analysis. Then using the mapping function and velocity component and coordinate point of detected particle to the velocity field from PIV analysis, the transformed data were also obtained and the speed was obtained and be mapped to object surface when the collected image was also obtained. So here we can see some images before collection for PIV major analysis. Then by applying this method, calibration method based on the ray tracing method, we can see that after applying our collection method, the size of vortex center and the velocity vector reduced towards center after collection. And also, as can be seen, the also processing result at almost same considering the particle study like aspect ratio and the refractive index. So to conclude, this with experimental visualization of internal flow for levitated and simulated droplet were performed, and the results show that the strong curvature distortion was found to occur under the higher refractive index and the aspect ratio, since they led to obstruct particle in the fluid droplet. And also to our result was compared with previous study, and the good agreement was with the work of Kang et al. And the analysis of accuracy of our calibration model was also quantified using by mean reprojection error. And also the size of vortex center and the velocity vector was found to reduce toward the center after collection. So thank you for your kind attention.
Thanks for your nice presentation. And has anyone has question? I have one question.
Okay, thank you.
I want to know how do you design your percentage about the water and gasoline. A percentage. Yes.
Designing what?
Percentage because can you put turn to page 8?
Okay, here. Okay.
Here.
Mm.
And the B figure you show the 24 percentage, right?
24. Oh, okay. This
Yes.
you mean? Okay. So normally here we were trying to mix up the glycerol and the water. So this percentage was the 24% of glycerol in the water and the 48% of glycerol in the water. So we were mixing to see by changing the refractive index and to see how the velocity, the refractive index can affect the curvature distortion, even the velocity vectors visualization.
Because the time, so sorry.
Okay.
Thanks for your interesting talk. Yeah, one quick question. So I see the droplet size is probably about the 4 millimeter size. So what's the droplet size? Yeah, what's the size of your droplet?
So the size of the droplet, if we measure, so normally to measure the droplet size, we use this formula. So since it is a leftated droplet, it can change with time and the form with time. Then use it by measuring the size of our droplet. It is easier to quantify the volume equivalent diameter of the droplet. And it was around the 3.5 something, yeah, for the water droplet.
So how small you think you can measure for the smaller size of droplet, because you are using the frozen particle to check the flow velocity inside the droplet. So I was wondering what's the limitation of your size, yeah, for your droplet.
So for the droplet size, I think any kind of size can be measured and can be levitated. But for our case, it was ranging from 2.5 to 3.5.
No, okay. Thank you very much. Yeah.
And thanks Gatete YouTube presentation again.
Thank you.
And this presenter is Yang Lai. Yang Lei.
Hello,
and
everyone.
His topic is heat transfer and flow characteristics of gas liquid two-phase flow in
能看到 PPT 吗？
in a rotating double cylinder. And let's welcome him.
Okay. Hello, everyone. Thank you for attending the meeting. And my search theme is heat transfer and cooling.
Sorry. Maybe you need to have the full screen of your PowerPoint.
Hey, what? You can you see?
你要把它播放全屏。
我已经全屏了呀。
重新试一下，从头来一下。
还不行。
把它关掉，重新分享。
我重新共有一下。 It's okay. Now, what happened? What happened?
Probably you need to choose the other window. Mr. Yang Li, can you see this?
Yes, hi. I don't know why. What happened?
Can you see this display?
Yes, I can see it.
Yeah, when you present,
Yes.
then you can choose which window you want to present, which window you want to share. So
Oh,
please
yeah.
choose the full screen of PPT one.
Maybe we need to wait a moment. I think.
Or you can choose at the most right side of the share screen window.
你别动，你别动。
我没动啊。
你
太可以。不行了。
你把这个停止，
停止，
然后关掉。你把这个关掉，别把这个打开。你这个别关啊，就刚刚重新来一个，就重新把这个步骤再走一遍。上次不就这么走的吗？对呀。然后共有呢？Windows，然后这个连进去，不行吗？
关上了。
要等一下，然后你，对，然后你再共享，共享你点呀。
What happened? Why?
我是现在，我跟他讲一下。Sorry，
你上传了吗？上传了，用上传的吧。就用办法
，maybe
就是用这个直接 share 这个 slide，对。然后，哎，就这个直接点从这点吧，你点一下试试，点右上角。哎，
不是。
哦，你要上传，你把你刚刚那个上传到这个上面，把你这个刚刚你这个 slide 上传，你等我一下 ，slide 点，然后点这个，然后把你刚刚那个上传一下。
哎，请问听得到吗？
喂，
听得到。我也不知道为什么这个。
那还是你先，
我们先进行下一个。
我先进行下一个吧。
再换你。
好的。
我先吗？
Sorry, because I had some problems. So we move to the next presenter is the Zhang Zhanpeng, and his topic is study of conjugate motivates heat transfer in open film. And let's welcome him.
Oh, hello. Hello, can you hear me?
Yes.
Okay, thank you. Chair, my presentation title is the study of multi-phase conjugate heat transfer in open form.
Sorry, you
you need to open your camera.
Oh, sorry. Sorry.
Okay, thank you.
Yeah. Today, I will give a brief introduction to OpenFOAM, and then I want to share how to realize the multi-phase conjugate heat transfer solver in OpenFOAM. OpenFOAM is an open source CFD software by finite volume method on Unix system based on the C++ standard template library. So it is an object-oriented program. The first advantage of OpenFOAM is obviously no cost because it is an open source software. And then the OpenFOAM also has the high readability and the various standard solvers. Firstly, I will take example to explain the readability of OpenFOAM course. Firstly, this is a code for creating the time mesh and field systems. This is very easy for everyone to understand, which shows the high quality of the OpenFOAM codes. And the second example is the discretization of the governing equations. And this is a simple unsteady diffusion equation. And the time derivative, which is showing the left part is ddt, and the second, and then the Laplacian terms and the source terms are all easy to understand. And the name of this class and objects are well arranged. We can quickly know that this is a scalar matrix based on the finite volume method. And its name is the T equation. So we can know that OpenFOAM codes have high readability. And then another advantage of OpenFOAM is the rich standard solver library. And these solvers shown here are varied in different areas and could be used directly with official cases. Here I will give some parts maybe used in research in thermal engineering, like the combustion, heat transfer, compressible and incompressible multi-phase flows, and so on. Here I need to point out that no multi-phase conjugate heat transfer solver in the standard toolbox, so we need to make such solver by ourselves. And then OpenFOAM also have some problems. Firstly, OpenFOAM does not include any graphical user interface, so you need to finish the simulation by commands in the Unix system. And then to compare with the commercial software, like the Camoso, has a very beautiful user interface, and you could obtain the help from the company side. And if you have any questions, so OpenFOAM may takes you more time to get used if you want to use it. And secondly, the insufficient documents. OpenFOAM has been developed for many years, so that it is now have many different versions. For example, the OpenFOAM Foundation version and the ESI version. These versions are later different with each other, and hence increasing your starting cost if you want to learn different versions. And then the guide of OpenFOAM is badly prepared. The source code of OpenFOAM we just mentioned has a very high quality, but its menu is not. So it is a challenge to understanding the source code. And then after that, as introduced above, OpenFOAM have not offered a standard solver for the multi-phase conjugate heat transfer issue. So now I want to talk about the evaporation phenomenon and show how many numerical techniques we need for realizing the simulation. Taking the boiling phenomenon as an example, look at this picture. This is a boiling phenomenon on the copper surface. The heat and mass transfer procedure is shown in the right diagram, and the heat from the heat source is generated in the solid part, and it is then to be conducted to the fluid part through conjugate heat transfer. And the working fluid, for example, water, is heated, and the evaporation or boiling happened. This is sorry. Oh, sorry. And is conducted the working fluid, for example, water is heated and the evaporation or boiling happens. This is a very strong phase change process with large amounts of heat. As generally, the heat will be dissipated to the atmosphere by some aqueous like condenser. So such issue could be described by the following governing equations listed here. Oh, I think you couldn't see the formula in your slide. Sorry, it may some problem. They included the three conservation equations, namely the mass, momentum, and energy equations. For solid parts, only the energy equation is efficient. And then we are faced with two problems: how to calculate the two-phase flow and the surface tension force. OpenFOAM offers at least two multi-phase flow model, the OLA approach and the VOF method. The first one is designed for the dense discrete phase flow, for example, the bubble flow. The second one is more focused on the interface capturing, offer the very clear liquid vapor interface. And here there is an example. This is a very classical multi-phase dam break case in OpenFOAM. The red color part is the air, and the left three colors are three kinds of liquids. The liquid will collapse under gravity, and the result is shown in the right. We can see that the second one is the bottom one is based on the VOF method, shows clear interface. Compared with the first one, you can look at the blue part. You can see that the second one is interface is more clear. So if you want to capture the interface for your multi-phase flow simulation, the VOF method should be selected. And in my study, the volume of fluid method is used for simulation, which could use the phase fraction alpha to break fluid into liquid, vapor, and the interface region. And the phase fraction equation, which is the key for the multi-phase issue and derived from the mass conservation, is solved in OpenFOAM based on the Muller's algorithm. I'm sorry, maybe it's just the sharing issue. You can see the formula. This method could give a high-end accuracy and make the solution strictly bounded between 0 and 1 because the alpha, the phase fraction means how much the liquid or vapor is in the one mesh, so that it couldn't lower than 0 or larger than 1. And then the surface tension on the gas-liquid interface is obtained by the continuum surface force model. This is implied in the OpenFOAM for the VOF method. In reality, the liquid-vapor interface is as same as a two-dimensional surface, so that across the interface there is no sudden pressure change. So, but this is a trouble for simulation. But by VOF method, it's impossible to obtain a real interface. Instead, as shown in the picture, the interface is a layer with limited volume. So based on the phenomenon, the CSF model could describe the pressure change by adding a pressure gradient from P air, P liquid to P vapor on the interface layer, showing in the red line in the right picture, and to converting the intermittent function of pressure into a continuous one. And then for the NS equations of that phenomena we mentioned above, there are transitions incompressible issues. So the energy equations could be segregated from the mass and momentum equation. Here you couldn't see the formula, but you can imagine that, because the density is all the same, so that the heat transfer does not make any effort on flow. So that is why the heat transfer equation could be segregated. But on the other hand, the velocity and pressure are coupled, and this is a classical problem for the NS equation. And in OpenFOAM, there are at least 3 ways, including the Peso, simple, and the Pimple algorithm, to solve the corporate NS equations. And among these three kind of ways, the simple algorithm is designed for the stable issue, so it's not be considered here. And the Pimple algorithm is put forward by OpenFOAM, which combines the pixel and the simple computations. Its advantage includes, firstly, to perform the transition step with a current number much larger than 1. As I know, based on the reference, it could be larger as maybe 50. And secondly, it could be used as the pixel loop. So if necessary, you can use the pixel form in the Pimple algorithm. And finally, for solving the conjugate heat transfer of a solid fluid system, in OpenFOAM, the segregate solution strategy is employed. And the red line in the left picture is the boundary between the fluid and solid. Firstly, we will compute the fluid system, fluid region, and then the boundary conditions for solving the right side, the solid part, are from the left fluid equations. And such loop will be done until the end, as shown in the fluid at the flow chart. And that is how this method realizes the computation of the conjugate heat transfer. As shown in the formula, the continuity boundary condition is used, and the temperature on the boundary and the heat flux across the boundary is kept. That is how OpenFOAM realized the conjugate heat transfer computation. So in conclusion, today I give a very brief introduction to OpenFOAM for simulation of thermal engineering issues. I hope it could help you to take interest in OpenFOAM. I just introduced some advantages and disadvantages of OpenFOAM. And here are some my personal thoughts about OpenFOAM. And firstly, although the standard solver library has included many solvers for different areas, the solver modification is still necessary in many cases. For example, the multi-phase conjugate heat transfer issues based on the VOF method. That is what I'm doing. So that this is just very common because OpenFOAM couldn't give anything. And that is just maybe a advantage of OpenFOAM, that it can give you a flexible code modification. And secondly, the OpenFOAM toolbox offer many classical algorithms. For example, we just talked about the VOF method and Muller's. However, it have not included some new algorithms. Here I give two examples. Firstly is the CLS VOF, and secondly is the Muller's CIC SAM. Both of them are the improved solver, improved with the VOF method, but it haven't been included in OpenFOAM. That is left for us. When you want to try some new algorithms, you can modify your solvers and use these algorithms. That's all. Thank you very much.
Thanks for your nice presentation. Anyone has question?
I have a question. So in your libraries software, is there or do you consider the energy or some things like thermodynamics properties, or yeah? So if that software can solve, so where's the database came from? Thank you.
Thank you very much. In OpenFOAM, there are some energy equations solver. It's maybe based on different kinds of database. First, you can use the standard database in OpenFOAM. OpenFOAM gives some standard the properties of many different kinds of species, but it's not very maybe it cannot qualify your stand or something. So in such cases, you can input your own database for your simulation. And also OpenFOAM give a lot of different kinds of energy solving algorithms. It can based on temperature or based on internal energy or entropy or any other kinds of energy formats. Thank you.
Is any has any question? Oh, okay, and thanks Zhang Zhanpeng again for the nice presentation.
Thank you.
And next presenter, we welcome the Yang Lei again. Yes, and his topic is heat transfer and flow characteristics of gas liquid two-phase flow in a rotating double cylinder. Let's welcome him.
Okay, hello everyone. Thanks for attending this meeting. And my thesis theme is heat transfer and flow characteristics of gas liquid two-phase flow in a rotating double cylinder. And rotating electric machinery such as EV motor and generators have a same problem. And heat is generated from electromagnetic steel plate and coils and during drive, and the heat will induce magnetic and the decrease and the increase of the electro resistance will reduce motor efficiency. As a result, efficient cooling method is required. And based on faster meters research result, the flow structure transitions from cold flow to VV vortex flow as the Reynolds number increases because of the centrifugal force acting on a flow mass is out of balance with the surrounding pressure. And based on the research result of USA, and the heat transfer is enhanced by convective heat transfer because of the tidal vortex flow and VV vortex flow. And based on the experiment of GDD, it suggests flow structure transitions can change at low Reynolds number in two-phase flows. Difficult from the existing study. The actual EV motor has complex structure with jets and use gas liquid two-phase flow with cooling oil inside the motor, and insufficient knowledge of the heat transfer and flow characteristics of gas liquid two-phase flow in a rotating double cylinder with jets. And the research objectives of this F1 study consist of the following two components: and illustrating flow structure of gas liquid two-phase flow in a rotating double cylinder with jets and heat transfer characteristics in a rotating double cylinder. The follow field in the motor is divided into main parts, and the gas area and the nozzle area. In this study, we use visualization experiment to analyze the flow structure in this area and the torque change in different parameters. In the future and in the future, I plan to use the simulation of the device to analyze the detailed flow structure and heat transfer characteristics inside the motor. And the dimension of the experiment are expressed as flows. The liquid flows into the rotor through the pathway inside the shaft, then flow into the gap space between the rotor and stator through the nozzle, and the effect of centrifugal force, and finally flows out from the drip under the effect of gravity and complete the cooling of the motor in this process. So maybe there is something wrong. They should be the. It's okay. About the visualization experiment in order to analyze, I divided flow field into the following 4 parts based on the position. As the result of visualization experiment of nozzle, and by increased rotation speed, the flow structure and transits to pattern 1, and due to the increase in flow rate, the liquid mix with air and transits to a bubble flow, and by the result of PAV, it suggests that the velocity of the liquid that jetted from the nozzle is accelerated under the influence of the centrifugal force. The measure velocity up to 10 times higher than the velocity calculated by the liquid single phase flow. This suggests that the volume fraction in the nozzle will be very high. And about the result of the visualization experiment in gap area, as the rotation speed increases, the liquid accumulation in upward part becomes more active. The rate of coverage of the liquid in the upward part increases, and the liquid is concentrated in the first half of the motor, and the coverage is evenly and distributed. And in the downward part, as high rotation speed and the liquid is wound up in downward path, the rate of liquid coverage is increases at high flow rate and high rotation speeds, and the range the range of saturation of the liquid current rate becomes narrow. This is concentrated to be and stabilization. About the flow doesn't wind up at about the torque, and the flow doesn't wind up at low rotation speed and becomes liquid pool. Concentrate force are small. This is no significant change in the flow structure with the increase of the flow rate, because as high rotation speed flow in the because as high rotation speeds fluid in the gap area becomes atomized, and the increase of the torque is suppressed. And finally, in the future, I made a plan to install of thermocouples and into the equipment and measure the temperature change at the difficult position of the motor during operation, and evaluate the effectiveness of the cooling system. And this is over. Thank you for everyone.
Thanks for your nice presentation. And is it anyone has question? Okay.
Thanks for your presentation. I'm wondering that can you turn to maybe page 12?
Page 12? This page.
Yes, this page. Can you explain what is the liquid cover rate?
And the liquid cover range is in the sorry, can you speak again, or what do you want to know?
Can you explain what is the liquid cover rate?
The liquid coverage is that the theta with the what should I say, is the theta is covered by the liquid, and the liquid cover what should I say? Sorry, there should be some picture to know what that means, but you know, you can't see that now.
Okay. I will help him. As he said that I'm not sure why, but the movie are on this slide, but we can we can show see the side view of the experimental setup, and we can find that there's a narrow films, I mean, liquid films are covered in a gap, and then we can measure how the area ratio. There's the total area over the liquid film covered area. So he said it is the definition of a liquid cover rate.
Okay, thanks. And the second question is, why only the 2 liter per minute goes down while the Reynolds number goes up, and the other is while the Reynolds number goes up, the liquid cover rate goes up.
Sorry, can you speak again? What?
I mean the red one, the 2 liter per minute points, the Reynolds number goes up, the liquid cover rate will goes down.
Yeah, yes.
And the other two, the blue one and black one, the Reynolds, while the Reynolds increasing and the liquid cover rates increase. Can you explain this phenomena?
Yes, you means as the rotation speed increase and the liquid coverage rate is also increased.
Yes.
You know the blue one.
I have the blue one and the red one. What's the difference between the blue one
The
and the black?
difference is because the liquid rate is difficult in a high rotation speed. You can see the picture. Certain you can see in the many and what should I say? Most about liquid and most of liquid is wound up into the downward path. So at the upward part, the liquid current rate is down, I think, in the upward part.
Okay, thank you.
Okay, because time up, so let's thank the Yang Lei presentation again. And next presenter is the Zhao Chengwei, and his topic is influence of surface structure and weightable on boiling heat transfer characteristics. And let's welcome him.
Okay. Okay, thank you. Can you see my PowerPoint?
Yes.
Okay, let's go. Can you see the full screen of the PowerPoint now?
Yes.
Okay, thank you. And it's my honor to be here for this presentation. Today, my name is Zhao Shenwei from the University of Tsukuba. Today, my topic
Sorry, can you speak louder?
Oh, sorry. It's okay, my voice?
Okay.
Okay, thank you. Today, my topic is the influences of surface structure and wettability on boiling heat transfer characteristics. As we know, boiling is a ubiquitous but very important physical phenomenon, and the boiling heat transfer is widely used in industry. For example, it is often used in the cooling process, such as the electronic devices. And pool boiling is a boiling of a heated water above saturation temperature immersed in a liquid. Usually, the boiling performance of a surface is shown by the boiling curve. This is the boiling curve. The part from point A, OMB, to point C, CHF is a nucleate boiling. It has the characteristics of low superheat and high heat flux. So in this experiment, we focus on the nucleate boiling. In this research, we mainly focus on two characteristics. The first one is the surface roughness RA, and the marine directions of RA is perpendicular to the processing direction of this surface. And the second characteristic is wettability. It is often expressed by the contact angle. The surface with contact angle less than 90 degrees is called a hydrophilic surface, and greater than 90 degrees is called a hydrophobic surface. About the previous research, in 2011, Professor Jules combined the boiling curves of hydrophobic and hydrophilic surfaces and found that the OMB of hydrophobic surface is earlier than that of a hydrophilic surface, but the CHF of hydrophilic surface is higher. And in 2017, Professor Kim found that the increasing the surface roughness of a hydrophobic surface could result in the decreasing of CHF. And in 2013, Professor Ettinger found that the boiling performances of the fitted surface is better than that of a surface with uniform wettability. And in 2020, Professor Ben also mentioned the befitted surface could increase the CHF and the heat transfer coefficient. So based on the previous research, the objective of this experiment is first, verify the befitted surface can enhance the boiling heat transfer. Second, optimize the pattern arrangement of the befitted surface. And in this experiment, the diameter of the copper is 13 millimeter. And this surface are named by the spots number, diameter, and pitch. And the air ratios is the proportion of the area of the hydrophobic spots on the copper surface. Surface fabrication. First, use the sandpaper of different specification to polish manually to make a smooth surface. And then add alumina suspension on lapping machine for secondary polishing until the surface is close to a mirror surface. For the coating part, the first is necessary to clean the surface and then apply masking films on the surface and then spray it with PTFE. And the coating surface should be dry in the air for 30 minutes and then heated for 1.5 hours. And in this experiment, the RA of individual surfaces is as close as possible. And the contact angle shown by these photos, the contact angle of PTFE spots is greater than 90 degrees. Well, that of a copper surface is less than 90 degrees. And this is the experimental setup. The main part is the boiling chamber, and the lower part is the heat transfer copper block surrounded by the thermal insulation material. And the heater 1 heat the heat transfer block, and heater 2 and 3 heat the liquid in the boiling chambers to maintain the temperature. To reduce the heat loss from the environment, an air heater is used to provide the additional heating. And there is a condensing device to provide the liquid circulations of the boiling chamber. And the vacuum pump used to extract the air from the device. The temperature of the heat transfer block and the boiling chambers are measured by these 5 key taps thermocouples, and the data is collected by the PCs from the data logger. And here, the 3 temperatures of the the heat transfer block are used to calculate the heat flux of the copper and heat flux of the block and the surface temperature by the Fournier's law. And in this experiment, by comparing the boiling curves of the copper surface and different bifida surface, we could find the bifida surface could significantly advance the OMB. And these right points are a different surface OMB. And moreover, at the same heat flux, the heat transfer coefficient of bifida surface is higher than copper surface. And these videos, we choose these three surfaces at the superheat of copper surface OMB, 8.96 degree. The two bifida surface has a higher heat flux, and there are more bubbles on the surface. About the fact of the pitch, although the OMB of the two surfaces is very close, as the heat flux increase, the heat transfer coefficient is higher on the surfaces with small pitch. And we can, in these two videos, we could find at the same heat flux, at the same superheat, the small pitch one has a higher heat flux and more bubbles on the surface. The next part is about the effect of the spot diameter. The OMB of D3 surface is a little earlier than the D2 surface. As the heat flux increase, the D3 surface has a slight advantage at a low superheat, at a low heat flux. And this video is like 2 points with a larger surface superheat surface heat flux differences. And at the close superheat, the D3 surface heat flux is twice that of the D2 surface. When the spot's diameter and pitch are fixed, I combine 4 bifida surfaces with different number of spots. For the experimental results, I found that surfaces with fewer spots perform better. But this is a little different from the Professor Zhu's result. And in his paper, the pitch between spots was 5 times of the spot's diameter. And his spot diameter was 100 microns. But in my experiments, the diameter is 2 millimeter and the pitch is 4 millimeter. And after checking these recordings, I think on the bifida surface of 9 and 16 spots used in this experiment, the bubble merging was more likely to occur. It's a result in the large bubbles in the early stage and a corresponding reduction in the vapor-liquid interface area. So it decreases the available surface area for the heat transfer and the frequency of the bubble generation. And finally, it results in a reduction of the boiling heat transfer coefficient. And for the proportion of the spot area, after comparing these 4 bifida surface and copper with different arrangements, and the proportions used in is ranged from 1% to 5.33%. We could find that the surface with the hydrophobic spot area of 1.33% performs best, but the difference between it and the 2.67% surface is not significant because this parameter is not very easy to control. I think it's maybe it's necessary to set some samples of different diameter of spot for the same proportions to compare the data and to compare data to find the effect of the air ratio gain. And we could not only use the thermodynamic calculation, but also record the bubble dynamics through the high-speed cameras. This is the 3D to P6 surface with the heat flux of 12 kilowatts square meters under saturated boiling conditions. In this case, the process of bubble generation, growth, and departure are shown by these videos and photos. By changing the liquid temperature and heat flux, the bubble departure diameter and frequency under different conditions could be obtained. And then we could use different models to combine this data. Conclusion. First, compared to a copper surface, a bifilar surface demonstrate an earlier OMB. Second, when the hydrophobic spots for the have the same diameter, decreasing the pitch could increase the heat transfer coefficient at low heat flux. When the pitch remains constant, surface with larger spots perform better at low heat flux, and the ratios of 2P seems to be variable related to the experiments. And last, about the effect of spot numbers, bubble merging may have occurred in the early stage and affect the experimental results. So it's necessary to increase the pitch of spot or reduce the diameter of the spot to about this situation. And this is my future work. That's all. Thank you for your kind attention.
Thanks for your nice presentation. Has anyone has question?
Okay, maybe I missed that. What's the working fluid you use?
I'm sorry?
What's the working fluid you use?
This application, it means working for
No,
the use?
What's the fluid?
Fluid, water. Distilled
Well, you
water.
just use the water, right? So,
yes.
You find that you use the PDF to coating the hydrophobic surface and to find the relation of the geometry and the size and the heat performance. But I think it's dependent on the property of working fluid, right?
Yes.
Can you hear me? Okay.
Yes.
So do you have any rational explanation on the surface geometry and the effects on the heat transfer performance? More rational explanation. Once you change working fluid, you find some size is the optimum, but once you change the working fluid, I think this size will be changed, right?
Yes, I think in this experiment, I just use the distilled water. Maybe we change some other fluid, field or liquid. These result may be changed. Yes, yes. But I think in this stage I just use the distilled water to find the differences between different surface, right? And maybe in other situation, yes, I think we can use some other liquid to have an experiment to find the differences between these liquid. Yes.
Okay, thank you.
One curious question. So you are using the spray coating to deposit your PTFE layers. Yeah. So have you checked the morphology? Sometimes I'm thinking about, is there any pinholes on your coating surface? So they will also have some hydrophobic phenomena on your coating surface.
Yes. I'm sorry, I can't hear clearly.
For your coating, for your PTFE coating.
Yes.
Yeah. What's the morphology of your coating? Is there any pinholes on your
Pinhole?
coatings?
Yes.
Yeah, there's more tiny holes in your coating layers.
Yes.
Yeah, so there will be also a hydrophobic layer inside those tiny holes. Yeah. So probably they are also nuclear the bubbles. I'm just curious about that.
I think, hmm, that means use the entire PTFE code. I'm
Yeah,
sorry, I can't.
but yeah, but for very detailed, I mean, microscope images, yeah, ideally should be I don't know, maybe you should expecting a uniform coding, but because there's a spray coding with PTFE, sometimes you will create some pinholes in the membrane.
I know.
I'm just curious about that. Yeah.
Yes, yes. I think if I use a substrate with the smooth copper and spray it with the PDFE, sometimes the surface roughness of the PDFE coating is also very rough. So I should take an experiment to test the entire PDFE coating surface. Yes. I think if I think in the previous researches, some professor have done some experimental experiment with the hydrophobic surface. Yes, entire set and uniform availability, and maybe how to say at the some higher heat flux, nearly about 600 kilowatt per square meter, the advantage of the PTFE is not used, is useless. Yes, I think when the heat flux increase, the is an advantage of PTFE coating is useless. So when use the PTFE coating for the befitted surface, just want to the first point we just want to advance the OMB. That means we can see the bubble in the early part of the nucleate boiling. Yes. So for sure, I think we should do some experiment with the whole PDFE coding. Yes, thank you for your question.
Okay, has anyone has question? Okay, let's thank the Zhao Chengwei again.
Thank you very much.
Okay, and this is the end of the section 4. Thanks for all participants to participate this students workshop, and let's welcome Professor Akiko Kaneko Sensei for the closing. Please applause for her.
Thank you very much for your kind introduction. Okay, and thank you very much. So finally, I will conclude this workshop as and the closing remarks here. And first of all, this is very we are very enjoy this workshop with many interesting topics, and we are spend a wonderful time and a very fruitful time, I think, and with full of hospitality. Okay, so here, let me briefly review this workshop. So I heard that today totally almost 50 participants today. It's a very great number, and also we have 7 presentation from National Central University, and from also 7 presentation from University of Tsukuba. And there's many topics like heat exchanger, heat pipes, some siphon battery, machine learning, flow boiling heat transfer, mass transfer with CO2, granular flow, and also the effect of wettability. And I think these energy issues are now global problem, as you know. And in this context, many up-to-date topics were covered this time, and a very good discussion were held. And I also believe that this workshop helped us to find the seeds to realize a good collaborative research or and the implementation between our two universities. And I was truly impressed to see many students conducted and the presentation very wonderful researches. And I understand that Professor Yan and your supervisors are very distinguished professors, and that you are in a very meaningful research environment here. But I would like to encourage all of you very talented peoples to do research in Japan also, to enhance your experience as researchers. So this is just a slide for recruiting for students. And we also have such a offers to kind of entrance examination for international students also. And if you are interested in, please take a look at the website or please contact me. And now I would like to present some information about the next workshop. Okay, so as Professor Yan said, the second National Central University and University Tsukuba workshop on summer energy technology will be held at the University of Tsukuba, Japan in next summer. And as I said earlier, there's a very research city, academic city in Tsukuba. So I think I would like to include visit to some of these institute in our lab tours also. And and also you can enjoy the Tokyo area, like this is Tokyo Tower and Akihabara. And also this is Asakusa. It's very close, almost 1 hour from the Tsukuba and the Akihabara. And also I think you can enjoy the Japanese culture, not only such a animation or such a very famous place in also the food and so on. And also if you have you have time, you can use Shinkansen to visit such a Kyoto. And I heard that some of you already visit Hiroshima, and I think you can use train to reach Kamakura or Fuji-san, Mount Fuji, and so on. So you can enjoy Japan also. Okay, so we are looking forward to seeing you next summer in Tsukuba. Thank you very much.
Thanks for Professor Kaneko Sensei for the closing remark. And the welcome party will be start at 5 p.m. So we just take a rest for until 5 a.m. and the party will at the fourth floor 452. So we can take a rest. So thank you.